So the structure of the review document, it looks exactly like an exam. This is the way your exam will appear. And let's see, before we go too far, let me scroll down to the bottom. Okay. These last pages, you'll have a periodic table always, and then you'll have other information. This is my useful information pages at the end. Anything that's at the end of the review document and useful information will be there on the exam. So this is stuff that you don't have to memorize, you just need to learn your way around. Okay, for naming conventions, these are polyatomic ions. Oops. There. These are polyatomic ions, and they're on the left-hand column, they're sorted by name, and on the right-hand column, they're sorted by formula. So it's the same information, just sorted differently on either side. Let's see. Now this one, this useful information chart will have things like equivalences, like 1 atmosphere equals 1 bar, which equals 101,325 pascals air pressure. Then you'll have some constants in here, like this one stuck up here at the top is the universal gas constant. You won't need it right now because we haven't got the gases. But these things are in there to, oh, how about the Bragg equation? And then the body-centered cube edge. Right? We talked about the spatial arrangements of the unit cell. This is one of them that tells you the length on the edge. If you know the radius of the atom in a body-centered cube, then that's your formula. Here's converts Fahrenheit from centigrade, Celsius. These are gas laws. You won't need them right now. Let's see. And then 1 atmosphere equals 760 millimeters of mercury. All you have to do, since I don't give a complete description of what these things are, you just need to know what they are, so that you can find them. You can recognize the information when you see it. Okay. And this thing's in Blackboard, right? You just go into Blackboard and it's obvious underneath exam 1, and then you have review documents, and it's all there. Okay, I think that's, yeah, okay, we'll go back to the top then. Okay, we're going to look at number 1 first. And this is chapter 10. So chapter 10, number 1. Which of the following should have the lowest boiling point? So we got to know what the question is. It's asking for boiling point. And out of these choices, which one is the lowest boiling point? So what influences the boiling point? The intermolecular forces, right? So the one that has the strongest intermolecular forces will have the weakest intermolecular forces will have the lowest boiling point, because the temperature of the boiling point is energy. Think of it as energy going into the system. And if you need to only put a little bit of energy to make it boil, then the forces should be weakest. So the weakest intermolecular forces will have the lowest boiling point. So we look at what we've got here. Sodium sulfide, what type of compound is that? Sodium sulfide is ionic. Okay. How about the next one? HF. HF is a covalent compound, but it's very polar. In other words, it has very strong, we haven't talked about electronegativity yet. It has a strong pull for electrons this way. It makes it very polar compound. How about ammonia? Ammonia is polar, right? And this is one of the reasons I picked this one out, because if you don't know these things, then you won't be able to assess the value. Oh, wait a minute. This is Chem 102. All this stuff was done in 101. Okay. So you have to sort of scratch your head, scratch your brain back to 101 and learn about polarity. Refresh your memory of polarity and a dipole moment. This has a pretty large dipole moment. Ammonia has somewhat of a dipole moment because it has a lone pair here, right? And it has a nitrogen there. In fact, this could be considered capable of forming hydrogen bonds, because each one of these is going to be slightly positive. And then, of course, you got the two lone pairs up here, so it's going to be fairly polar. Now, since we're looking for the weakest intermolecular forces, it probably doesn't matter that these are slightly different from one another, or that ionic compounds are hugely strong intermolecular forces. So the boiling point here is going to be massive. So what's the next one? Dinitrogen. Dinitrogen is like that, right? That is non-polar. And then F is water. So water is polar, and it also is capable of H bonds, hydrogen bonding. So based on this information, it's fairly easy to figure the weakest intermolecular force is going to be this one, the non-polar molecule. What forces does it have available to it? The only thing left is dispersion, London dispersion forces, and they're very, very weak. So E should be, oh, D, excuse me. Can you spell? Know my alphabet, A, B, C, D, E. Okay, does that make sense to everybody? Okay, that gives us a review of intermolecular forces and their relationship to boiling points. But that can be expanded to any of the measurements that we did: boiling point, freezing point, vapor pressure, those types of things. So let's look at number 3 now. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? Okay. So I find it always helps to draw a picture. There's your water molecule. Remember, it's bent, and it has lone pairs up here. So this end is going to be slightly positive. This end is going to be negative. So what's involved in the bonding, the hydrogen bonding? Well, when two water molecules approach one another, if they approach hydrogen to hydrogen, they're going to repel, correct? Or if they approach oxygen to oxygen, they'll repel. I mean, it's simple electrostatics. So what you want is another oxygen here, like that, because it's got the negative, and these have the positives. So now we can answer the question. You just have to pick the right one. A hydrogen from one molecule and a hydrogen, nope, because they're both positive. They repel. A hydrogen from one molecule and an oxygen from the other molecule. Well, yeah, we found the right answer. So test taking technique, unless you have one down here that says all the above, none of the above, two of the above, those kind of messy propositions. If they're all unique answers, then once you find the right one, going A, B, C, D, find the right one, you can stop. But if you want to be certain, C says an oxygen from one molecule and oxygen from the other. Nope, they repel. Those two are the same charge, they repel. An oxygen and a hydrogen from the same molecule, that's going to be kind of hard to do. On small molecules like this, you'd have to bend that bond around like this, and that ain't gonna happen. Now, large molecules, sometimes it does happen, because large molecules can bend around and interact intramolecularly. And not just this type of bit. That's tricky with our language. Intramolecular we think of as the covalent bond. But intermolecular interactions do occur for large molecules. But we're not going to do that. We're going to stick with the small ones for now. Two hydrogens from one molecule, one hydrogen. No. Repulsion again. So that's the basis for the answer. Which sides of the molecule attract, which sides will repel one another. So that's why the answer is B. Okay. Let's see. So next one I marked off. Okay. Number 4. Let's scroll down. Here we go. Okay, so number 4 is based upon these drawings, right? Roman numeral 1, 2, or 3. So it may not reference all of them. Maybe it only references one of them. So let's read this one before we scroll again. I think there's anything I can do about that. Oh, unless I do this. Oh. This is finer control. Okay, there we go. So now we can see our choices here. Which one is it referencing? Which of the following statements are incorrect concerning drawing 3? So we only have to look at this one. So it may be hard to see, but this is a chlorine and that's a hydrogen. So what we're looking at is, let's see, this is number 4. What we're looking at there is a hydrogen with a chlorine. All right, so which one's going to be negative? Which one's going to be positive side? Well, the chlorine is more electronegative than hydrogen. So it's going to be slightly negative, and this is going to be slightly positive. And I think that's what's shown. Yes. So that's what we would expect. Now, are they behaving correctly? It appears. Hydrogen on this side, then chlorine, then hydrogen there and chlorine. So you're getting positives and negatives interacting. All right, let's look at our statements. Which of the following statements are incorrect? So it looks like this one says 2 of the above statements are incorrect. So that means we've got to go through all of them. Electrostatic interactions exist between the molecules. Is that true? Well, yeah. They have a slight distribution of negatives toward the chlorine. So you have the potential for electrostatic attraction. So A is true. About B, the molecules find the best compromise between attraction and repulsion. Now, as a blanket statement, we can say that's always true. The best compromise between attraction and repulsion means that the system tends toward lowest possible energy. When you have repulsion, then the energy goes up. So it's going to find, the molecules are going to find the best compromise between attraction and repulsion. C, these molecules exhibit ionic bonding. Is that true? No, because they're not ions. Right? There's only a slight negative charge and a slight positive charge on this side. In order to have ionic bonding, you need complete ions. That is, this one, say, has to give up an electron, and this one has to accept the electron. Now you have complete ions. That means at least one electron, possibly more, are transferred completely from one to the other. Then you have ionic bonding. Otherwise, you simply have a dipole-dipole interactions. a partial redistribution of charge. So C is false. How about D? So C is one of them. It's an incorrect statement. OCS exhibits this type of interaction. Okay, what do we mean by OCS? Well, OCS is like that, and like that. Okay. We could draw the Lewis dot structure for that if we wanted to. But if you just look at the arrangement, oxygen is more electronegative than carbon, and it's a little bit more electronegative than sulfur. But sulfur is more electronegative than carbon. So we probably got the positive in here and the negative here, although this one is a greater negative than that one. So you have the potential for this similar type of interaction. All right, so the only one that's false is C. This is not ionic bonding. All right, that was number 4. Let's see. We're going to go down to number 6 now. There it is. Good. Got the whole thing on one page. Which best explains the following trend? 6. So what's the trend here? I mean, if the question is the following trend, we need to find out what the trend is. So what's the trend? Well, if you move down, notice that these are all noble gases. And they follow from top to bottom the same direction and same position as the periodic table. Right? So this one's the smallest of the noble gases, and this one is bigger, and this one's bigger yet, that one's bigger, this is the biggest. Okay? So what's the trend? As we increase atomic number in this group, we increase the boiling point. So what does that mean? Remember, as you increase the boiling point, that means there's more energy required to make that substance boil. In other words, the intermolecular forces are stronger as you go down. That's the trend. This is the obvious trend. This is the measurement that was made. The temperature of the boiling point. But the reason for the boiling point is intermolecular forces. They increase as you go down. Right? So what type of intermolecular forces are we talking about here? Well, these are individual atoms. Right? You can't do polarity with one atom. Right? The best you can do with one atom is London dispersion forces. So what you got is with helium, neon, argon, krypton, and xenon, you got a tiny atom there, and you got a bigger one here, a bigger one there, bigger one there, and then a huge one here. Okay. So relative sizes. So what that means is, since London dispersion forces are caused by instantaneous redistribution of electron density, if you have a larger space for them, and actually more of them away from the nucleus, then you have more, the probability of redistributing electron density is higher for the larger atom. Right? It's much easier to get these separations, instantaneous separations, for a larger atom than it is for a smaller atom. So we're looking at London dispersion forces increasing as you go down. Okay. So now let's look at the, which explains the following. Oh, well, the first one answers our question. London dispersion forces explains this trend. You can't have dipoles because they're single atoms. You can't have hydrogen bottoms. There's no hydrogen there. And Le Chatelier's principle is just kind of thrown in there as a confusing statement, right? Le Chatelier said nothing about this stuff. And then none of these. Well, actually, A explains it perfectly. Okay, that was 6. Oh, we get lots of time because we're not going to do a lab today. Okay, 7. We'll just leave it like it is then. Stop me anytime if something is not clear. Which of the following compounds has the lowest viscosity? Okay, lowest viscosity. So think about what causes viscosity. Higher viscosity means stronger intermolecular forces. So the lowest viscosity would be the weakest intermolecular forces. All right, what are our choices? All right, we have A, carbon tetrachloride. We have B, nitrogen gas. C, water. Liquid. Let's see, yes, we are given the phases. This is a liquid. And D is CH3, CH2, 25, CH3, correct? Liquid. And E, HCl, gas. Okay. So which of these would have the lowest intermolecular forces? No, the lowest viscosity. Lowest viscosity. The highest viscosity is more like molasses in winter. The lowest viscosity would be gas. Yeah, one of the gases. So let's see, we got a couple, right? That's good. Process of elimination, right? Throw out the liquids, throw out the liquids, throw out the liquids. Deal with the gases. They would have the lowest viscosity. So then we just have to choose between these two. Well, this one is going to be a polar molecule. Nitrogen is nonpolar. So there's your answer. Nitrogen would have the lowest viscosity. While we're here, which one would have the highest viscosity? Well, let's see. Throughout the gases, liquids, carbon tetrachloride is a nonpolar molecule. Remember, it's a tetrahedron. And then in the back. So it's going to be nonpolar. Water will have a higher viscosity because it's polar. But this one, even though this one is not polar, and it only has London dispersion forces at its disposal because all of these carbons, all these positions along here are polar, because it's such a huge molecule, then the London dispersion forces add up. And actually the viscosity of this one is greater than it is for water. This is probably we're probably getting close to asphalt here in the hydrocarbon, the homologous series of hydrocarbons. You know, you start off with methane, and then you get 2 carbons, and then you get 3 carbons. Let's see, 8. And you just keep going. And you get up to this one, which has 1, 2, 27 carbons. So that should be 56 hydrogens. Add them up, see. Well, that's 50 plus 3 plus 3 is 56. Okay, so once you get this big, the London dispersion forces really add up. And this is actually thicker than water. But that wasn't the question. I just thought I'd make a point. Okay, that was 7. Oh, 8. Let's see. Okay, 8. We can still see 8, so I'll just leave it alone. When a nonpolar liquid displays a convex meniscus. We're talking about a liquid here in a tube and has a convex meniscus, but it's nonpolar. A nonpolar liquid has a convex meniscus. What does that mean? Which of the following explains this behavior? Remember, there's a tug of war between adhesion and cohesion. Of course, cohesion are the forces that are active among the liquid molecules that hold it together. Adhesion are the forces that are attracting this liquid to the container walls. So there's a battle going on here. So when you see this, then the internal forces are winning. The cohesive forces are stronger than the adhesive forces. Think mercury. So let's see, which one of these explains it? It has a low surface tension and therefore clings to the glass. Surface tension has nothing to do with this. The cohesive forces are stronger than the adhesive forces. That's your answer. Cohesive forces are stronger than adhesive. C is just the opposite statement, so they can't both be true. So C is wrong. The liquid's viscosity is low. It doesn't say anything about viscosity. In fact, you can't tell anything about viscosity by simply looking at that example. In order to determine viscosity, you need movement. In other words, you're going to let this stuff drip through a sieve or drop a probe into it and see how far the probe goes. There are various types of instruments that measure viscosity. Let's see. Come on, there we go. Okay. So that's why the answer is B for number 8. The tug of war between adhesion and cohesion. So far, our discussion has been completely about intermolecular forces, which makes sense because that's chapter 10. All right. Well, let's see. We're going to just stick with 9. Let's see, 9. Let's see if I can get that whole page on here. Then I won't have to flip and scroll. No, I'm going to have to go down. So we'll do the ones that I can see so far. 9. I want to do 9. Yes. All right. Which substance can be described as cations bonded together by mobile electrons? Cations bonded together by mobile electrons. So we got these positive charge things, and we got electrons that are just going anywhere they want to. All right. So what would be which substance can be explained as bonded like that? Well, these guys are either, well, let's see, let's start from the bottom. HCl, liquid hydrogen chloride, that is a covalently bound molecule that is polar. So that doesn't explain the free electrons. KCl doesn't have free electrons either. Chlorine has them all. The potassium gave them up. So there are no free electrons here. Krypton is a noble gas. It's not going to turn loose of its electrons under almost any circumstances. I mean, we can force it to bond, but even then, when krypton is forced to bond with something like fluorine, it's a covalent bond, right? There are no mobile electrons there. How about S8, which is sulfur? It's one of the allotropes of sulfur. It has 8 sulfur atoms bonded together covalently. There are no free electrons there. The only one that fits is metals. This is one of the explanations for why metals bond, the metallic bond. It was an early explanation of why metals bond, but it's not the best explanation. In order to get the best explanation for metallic bond, you need the molecular orbitals. But this is one explanation, and it fits nothing but in here except silver. All right. How about, let's see, what's next? 10. Which of the following statements about steel is false? So we have to be sure and understand the question. We're looking for the false statement. This one says all of them are true. So we have to look at every statement. How about steel? It contains carbon atoms in the holes of its ion crystals. That's true. It's an interstitial, right? An interstitial alloy. The carbon atoms are in here. Like you got iron, 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 like that. In its unit cells, and then we stick carbons in the holes. So that's true. Let's see, here we go. How about the second one? The presence of carbon ion bonds in the alloy makes steel harder and stronger than pure iron. Yeah, carbon iron bonds. So it doesn't just sit in there. There are bonds formed here, and it tends to lock the crystals in place. They don't move, so it makes steel harder than pure iron. If you've ever seen a sample of pure iron or had to hold one, you can scratch it with your fingernail. It's so soft. So B is true. Pure iron is relatively soft and ductile because it lacks directional bonding. That's true also. Right? It's bonded in every different direction, but they're all weak bonds. And if you think about iron, based on our previous discussion, number 9, you've got these cations floating around in free electron soup. And there's nothing really holding them together. They just sort of, they slide past one another very easily. In other words, you can hammer them cold and they'll move. Now, if you're going to make something out of steel and you want to hammer it, you got to get it hot. Okay, so that was true. How about D? The amount of carbon directly affects the properties of steel. That is definitely true. Anything 0.5% carbon or greater. Now that might run down to 0.3 to 0.5%, I think, for carbon is considered high carbon steel. Anything below that is low carbon. And it changes the nature of the steel. When you get high carbon steel, it can keep a very hard edge, but it's not tough. It's easy to snap it off. I mean, you can break your edge. So when the katana is forged by Japanese metalsmiths, they combine 2 metals. They have soft steel and hard steel. And they combine them in such a way that the soft steel is internal and toward the back to give some flexibility and toughness to the blade. And then the edge is high carbon steel, and it's tempered a certain way, right? If you've ever looked at a katana blade, you see you fall down the blade. Let's see, it's curved, and you'll see this kind of a squiggly line here. When they finish the blade, the last time they heat it up and quench it, they pack a wet clay on it, on this side, and let it dry. And they heat it up in the furnace. And then when they quench it, that clay prevents this side from cooling too fast. But this quenches really fast, and that locks the crystals in place. It makes them very hard. So this is the high carbon steel, and this, in conjunction with the low carbon steel, gives you a blade that's both tough and sharp. Nowadays, we can duplicate the effect and just the type of alloy you choose to make the blade. You can make the blade out of the same material and get both toughness and sharpness of your blade that the ancient Japanese weren't able to master. Okay, so all of these are true. All of those statements are true. That was number 10, 11. Let's take a look at 11. Which of the following statements is true about P-type silicon? All right. Here's silicon. Okay. Remember, silicon is right close to this, this metalloid line right here, the breaking point between metals and non-metals. Of course, Elizabeth can't see what I'm doing here, but I'm illustrating the position of silicon in the periodic table. It's right on that line on the non-metal side. It is, in fact, a metalloid. Sometimes it acts like a metal, sometimes it acts like a non-metal. But for the semiconductors, what we need is, you remember that silicon, if it's charged, it could be a +4 or -4. It's 4 valence electrons. That's the key. 4 valence electrons. Okay, so if you combine it with anything that has fewer electrons, it will give you a p-type. So fewer electrons gives you a p-type. But that just refers to positive, as a positive nature. So which one has fewer valence electrons? Anything to the left and below that line from silicon. So we could dope it with aluminum, we could dope it with boron, or we could dope it with gallium would be a good choice. So with that being said, let's see which one of these statements is true about p-types. It's produced by doping silicon with phosphorus or arsenic. All right, where is phosphorus and arsenic relative to silicon? Phosphorus to the right, arsenic to the right and below. That won't work. They both have 5 valence electrons. So they have 1 extra electron. That's actually makes an N-type semiconductor. So that's false. How about B? Protons are the mobile charge carriers. No, protons never move. Protons are in the nucleus of the atom. The only thing that moves is the electron. So when semiconductor engineers talk about N-type, actually they use small n, N-type semiconductors, they're able to say that electrons move. That's easy to understand. But when you're talking about p-types, they say positive holes move. Okay. They say the positive holes move. Actually, what happens is the positive hole's here, and electron moves in from here, which leaves a positive behind. So the effect is movement of the hole, but actually the electron moved. So protons do not move. Remember what we said, if a proton moves, it has to come from a nucleus, and if it comes from any one of these nuclei, it makes a new element, makes a different element. So that can't happen. It does not conduct electricity as well as pure silicon. Actually, it conducts electricity better than pure silicon because you have mobile charges, right? Either one of them, you have mobile charges. They're not conductors. In other words, the electrons do not move freely like in a copper wire, but they can move. And because they can move, you can combine one type with the other and make logic gates, for instance. Sometimes they're volatile, sometimes they're permanent, or they're EPROMs, right? Programmable. Okay, let's see, where did we get down to? Well, E, none of these are true. These are all false statements. And the reason we know they're false is because first we looked at the background, right? What is a P-type silicon semiconductor? Then we could say, all right, now that I understand what it is and how you make one, then you can look at the questions and eliminate them one at a time. Okay, that's 11. I'm going to skip down to 14. Let's see if I can do it without. Yeah, there's 14. All right, a solid crystal of sodium chloride. We have sodium chloride solid. And look at each one of these statements and see what, right? Look at what the statements are saying. It looks like it's a dual statement. Each one says something about melting and about electrical conduction. So we look for ones melting, right? So we want, well, actually, it says three things. Excuse me, three things. This characterizes ionic compounds, solid ionic compounds. They're hard, right? So it's either B or D. They have high melting points. Let's see, B is high melting, D is high melting. Okay, so we're still either one of those. Then it's a good electrical conductor, or it's a poor electrical conductor. What do you need for a substance to conduct electricity? You need mobile charges, either positive or negative, doesn't matter. So solid sodium chloride, this crystal, is a poor electrical conductor because these ions are locked in the crystal. They're locked in place. Right. At the corners of this, if you ever spill salt on a table, look at it with magnifying glass, you'll get a clue as to the structure of sodium chloride. They're little cubes. Right. So you go like that, like that. And this is going to have a sodium over here. This is going to have a chlorine over here. This is going to have sodium over here, sodium here, chlorine here, chlorine here. 1, 2, 3, 4, 1, 2, 3, 4. Okay. So these ions are locked in place in that simple cubic lattice. They can't move. That's why sodium chloride is hard, high melting, and a poor electrical conductor. Now, if you free these charges up, then they'll move and they will conduct electricity. Say if you put sodium chloride in water, pure water is an insulator. It will not conduct electricity. But if you put sodium chloride in there, then the sodium and chlorine ions separate. And now they're able to conduct electricity. So salt water will conduct electricity very efficiently. Or you can melt it. If you melt it, then these ions are able to move. And there are nuclear reactor designs that use liquid sodium chloride. Actually, that's theoretical. They get better heat capacity from liquid sodium. Just take sodium and liquefy it. And it's very good at transferring large amounts of heat. Has very high specific heat capacity. Anyway, so the answer to this one is D. It's hard, high melting point, poor conductor. All right, that was 14. Let's see where we're going next. Oh, we're going 15. Where's 15? 15's down there. Let me scroll up on that. Maybe we can get it. I think 16 is also on the agenda. There we go. There's 15. I wonder if I can make that bigger. Let's see. I don't want to make it too big, but yeah, we can still see it. So I'm going to what? 15, 16, 17. If we can get those three on there. 15, which of the following is the highest melting temperature? This is kind of redundant. You really want to look, if you're looking for the highest melting temperature, you want to see if there are any ionic compounds in there. If you've got ionics in there, then you can throw the rest out. And it looks like we do magnesium fluoride. Right there. Very high melting point. It's ionic. So why is it, would this be relative to sodium chloride? Would this be higher or lower melting point than sodium chloride? Remember the conditions for melting point? Ionic charge and ionic size. So if you have high charge, small size, you get more electrostatic attraction, which means higher melting point. So magnesium is 2+ charge and is right next door to sodium. It's got more electrons, right? Remember the atomic size as you go from lower left to upper right. Let's see. Go down, the atomic size increases. And as you go to the right, it decreases. Right. So magnesium is to the right of sodium. It should be a smaller atomic size to begin with. And then you take away 2 electrons and shrinks it even further. So this ion is smaller than sodium, right? Plus it has a 2+ charge. And then fluorine is even smaller and smaller still with minus charge each. So this one is going to be higher melting point than sodium chloride. Oh, but to answer the question, well, we did answer the question. D had the highest melting point, magnesium chloride. I used to operate an analytical instrument, inductively coupled argon plasma spectrometer, which is a fancy name for it. We used a induction coil with very high magnetic strength, and we blast argon through it. And once you seed it with ions, then it will couple with that magnetic flux, and it gets hot. It's like 10,000 K. And you squirt your samples into it, and it just rips them apart. Electrons separated from their nuclei, and then further up in the torch starts to cool down. Then the electrons return. And as they return, they emit light. And that's the light we're looking at. Well, we want to look at vacuum ultraviolet type wavelengths between 150 to maybe 250 nanometers. And most optics, glass optics, will absorb that light. So the lens in that instrument was made out of magnesium chloride. Okay, you had to be careful with it. I mean, it had a high melting point, but it was easy to scratch. So you had to be very delicate. You had to handle it carefully. But of course, it was perfectly suited for this instrument because any radiation coming from that torch would not be enough to melt it. Okay, let's see. What's next? 16? Okay. Number 16. How are we doing on time? Okay, we killed an hour. I was at check myself. 10:50 for the lecture. Okay, 16. Which of the statements is false? So none of the statements is false. That means we got to look at every one. A, B, C, and D. Diamond is a covalent crystal. Is that true? Yeah. It's an allotrope of carbon, and it has each carbon is bound to 4 other carbons covalently. And then this one is bound to 3 others in that direction. In fact, it's a molecular solid. And if you were fortunate enough to own a diamond that is flawless, and you could shrink yourself down small enough, you could walk from carbon to carbon to carbon from one side of that crystal to the other side and never get your feet wet. In other words, there'll be no breaks. So A is true. The size of the unit cell of lithium and cesium is the same. Is that reasonable? The unit cell, the size of the unit cell for lithium is the same as cesium. Well, look at the periodic table. Lithium is way up here, right? Atomic number 3. Cesium is way down here, atomic number 55. That cesium atom takes up a huge amount of space, just sitting there on its own. Put it in a crystal, and it's going to take up even more space. So that can't be true. The size of the unit cell has to be bigger for cesium than it is for lithium. Simply because you've got, let's say, lithium is in the 2nd period, cesium is in the 6th period, right? You're talking about you've added layers of principal quantum number all the way up to 6. So B is false. Now, if B is the only false one, then we don't have to pick E. So molecular crystals usually have low melting points. That's true. Molecular crystals have a low melting point if they're not completely covalently bound. And what we mean by molecular crystal is the molecules are covalently bound, and they attract one another by these intermolecular forces, which are usually weak. So, for instance, a molecular crystal would be ice. We have water molecules that are attracted to one another, and they form that hexagonal crystal structure. We can melt ice at 0 degrees Fahrenheit, Celsius, excuse me, 32 degrees Fahrenheit. So they have very low melting points. That's true. Metallic crystals are usually good electrical conductors. That's true. Remember the theory of the cation surrounded in a electron soup. Those electrons are free to move. So metallic crystals are usually good electrical conductors. So the only false one in there is B. Okay, that's 16, 17. We're gonna look at 17 also. And we're still in chapter 10. How would you expect the melting point of carbon tetrachloride to compare to sodium chloride? Well, sodium chloride is an ionic compound, has a very high melting point. Carbon tetrachloride is a nonpolar covalent compound. So it has only access London dispersion forces. So it should have a lower melting point, but it looks like there's more to it than that. So we're getting an explanation at the same time. So it should be lower, right? Because sodium chloride forms an extended ionic crystal lattice. Well, that's true. Whereas carbon tetrachloride is covalently bonded small molecule. Yeah, in fact, you would have to lower the temperature way, way down to get solid carbon tetrachloride. So that's true. Let's see, what are the other statements? Not possible to say anything about that, so we throw E out. We've already said something definitive about it, and A appears to be the answer. Let's see what B says. It should be similar since they are both, no, they're not ionic solids. That's kind of a stupid statement. It should be higher. Carbon tetrachloride higher because of, no. Now, it would take more energy to break those covalent bonds than it would to separate these ions. That's true. The individual covalent bond is stronger than the ionic bond. But this crystal lattice allows the form to change. In other words, the phase can change from solid to liquid easier for this covalent compound than it will for an ionic compound. That kind of spins your head around it if you don't stop and think what we're saying. We're just breaking the bonds between individual carbon tetrachloride molecules. Over here, we've got to disrupt the crystal lattice between sodium and chlorine ions. So B is false. It should be higher because the bonds are stronger. No. Actually, this is apples and oranges. These two statements are talking about different bonds that would be broken. In other words, the bonds that they're talking about are the covalent bonds that hold carbon tetrachloride molecule together. Whereas here, we're talking about intermolecular forces. It should be higher because, well, no, it's not higher for any of these reasons. Because carbon tetrachloride is larger than sodium chloride. That has nothing to do with it, not in this case. So A is the only answer that's true. We skip 18. Let's see. Yeah, okay. 18 will go to 19. I didn't even write that other one up here, did I? Normal atmospheric pressure and temperature of 0 degrees Celsius. Which phase of water can exist? At 0 degrees, okay, and 1 atmosphere. Okay. Which phase or phases of water can exist? This is the freezing point, correct? At 1 atmosphere. Okay. So what can exist? Remember that diagram. This is time, heating time. So you're adding heat as you go that direction. And this is temperature. So you get solid being heated, and then at the melting point, 0 degrees, is constant temperature until all the ice is melted, and then it starts heating again. Liquid water heats, and it goes on up. And when you get to that point, 100 degrees Celsius, this is solid, This is solid and liquid. This is liquid. This is liquid and gas. And then this is gas only. So whenever you've got a phase change going on, the temperature is fixed because all of the energy you're putting into it is going into the process of melting solid to liquid. So at 0 degrees, which phases of water can exist? Both these, solid and liquid, right? Let's see, ice and water. And here I assume that when they say water, they mean liquid water. Okay. Let's see, 20. Okay, which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? All right, so we're using terms here that we didn't completely define in the lecture. So let's say we have, let's see, what number is that? 20. Here are the terms. All right. So you have solid here, and then you have liquid over here. I think that's the way I've got it arranged. Oh no, excuse me. Yeah, solid here. We got a liquid here. And then we got gas over here. Okay? So they can go backwards and forwards between each. Either solid can become a liquid or liquid can become a solid, phase change. But the descriptive term for each is if you're going this way, this way, this way. We'll do that one first. So liquid to solid, get the terms correct, is called fusion. I'm talking about nuclear fusion. I'm talking about the liquids, molecules come together, they fuse together into a solid. Sometimes we refer to it as freezing. A solid to a gas, going straight from a solid to a gas is like dry ice, carbon dioxide. From a solid to a gas is called sublimation. Okay? And then from a gas to a liquid is called condensation. Pretty sure. Yeah, condensation. Okay, so we can go backwards. Liquid to gas is evaporation or boiling, either one. If it's not boiling, then evaporation is the best. If you're not at the boiling point, then you get evaporation. But if you're at the boiling point, that's what you say. We go from gas to solid, it's called deposition. Okay? And if we go from solid to liquid, it's melting. I think that's the only term that applies. Yeah. So there you have your descriptive terms for each of these processes. Now we can look at the question. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? Evaporation. Here we go. So evaporation and condensation occur simultaneously when you measure vapor pressure. So there you go. E is condensation. This is just a matter of knowing what the words are, memorizing the words and what they stand for. So evaporation and condensation are converses. Sublimation and deposition are converse. Fusion and melting are converse. All right. So let's see what's next. Let's see, 21 and 22. I got those bracketed, so they must be similar concepts. Let's see what 21 says first. And anything I put up here, I want to erase until we've done 22 to see. Okay. 21. You are given the following boiling point data. Which of the liquids would you expect to have highest vapor pressure at room temperature? So think about what vapor pressure measures. Vapor pressure increases as intermolecular forces decrease. So this is going to go up when the forces go down. All right. So how do we measure those forces? Well, one way is boiling point. So these are the boiling points, right? Following boiling point data. The higher the boiling point, the higher the forces. So we're looking for the lowest forces to get the highest vapor pressure. So the lowest forces would be the lowest boiling point. So 100, there's 100 for water, 198 for ethylene glycol. That's your antifreeze in your radiator. So it looks like diethyl ether, D, would have the lowest intermolecular forces, would give you the highest vapor pressure. Diethyl ether. Right? Ethers are all like this. And then ethyl would be this is the way you write organic molecules convention. These hydrogens are bound to that carbon. They're not bound to this carbon right here. They're bound to this carbon. And these carbons are bound together. It's just conventions for writing organic molecules. Okay, before I erase that, let's see. 22, which of the one of the following decreases as the strength of attractive intermolecular forces increases? Okay. So we can't do that separately. Remember that closing slide that I showed you? There was only one in which the physical change was decreased as the strength of the attractive intermolecular forces increased. If the forces are increasing, they're holding the molecules together. So melting point, stronger forces, higher melting point. Stronger forces, higher boiling point. Stronger forces, lower vapor pressure because the molecules can't escape into the headspace above. So we're looking for vapor pressure. Which of the following decreases as the strength of attractive intermolecular forces increases? So that's the vapor pressure of a liquid. That's the only one that decreases with stronger intermolecular forces. All righty. Oh, 23. Before I leave this page, let's see. Oops. Too far on the scroll. There we go. 23. In which of the following processes will energy be evolved as heat? So we're talking about exothermic. And you remember, let's see. We did that first semester, I think. Verify. I don't want to talk about something we haven't discussed yet. Yeah, we did calorimetry in the first semester. So heat is evolved. That means what? Delta H is negative. Under what circumstances? Well, if heat's going to be given up, That means during the process, the system becomes more stable. So liquids become solids, gases become liquids, that's more stable. And with these types of references, these types of processes, excuse me, you're looking for the one that goes from higher energy phase to lower energy phase, because then it would give up energy, exothermic. So let's see, what happens in sublimation? Sublimation, you go from solid to gas, right? That takes energy. That's why dry ice is cold. It's carbon dioxide, liquid, solid carbon dioxide is minus, let's see, minus 78.5 degrees Celsius. So it's really cold. Crystallization. Crystallization, you're going, now we didn't talk about this process. Crystallization is a type of deposition. In other words, if you've got separate ions here, and they're making solid sodium chloride, that's crystallization. But in chemical terms, to actually measure this needs to be a gas, and this needs to be a gas. But this delta H will be negative because these are high energy. They're coming together for in a more stable configuration, and they give up energy. So crystallization is the answer to this one. We get an exothermic reaction. Vaporization requires energy, going from a liquid to a gas. That's why water on your skin, as it evaporates, cools your skin. You can feel it cool. Melting, right? You go from ice to liquid water, takes energy. That's why it cools its surroundings. Makes my drink cold. All right, so B is the answer to number 23. Let's see. We're going to skip 24. We're going to do 25 and 26. Let me scroll down to be sure I get both of them on the same page. I'm not going to. We'll have 25, and then we'll have to scroll to 26. This problem revolves around interpreting graphs, phase diagrams. Okay, choose the correct statement about the diagram below. Now, what we have to do is look at this diagram carefully because it's missing information. Right? It doesn't say what the temperature is, but the temperature is on the scale, and it's increasing from left to right. There should be an arrowhead there. And this is pressure increasing from bottom to top. And this is the 1 atmosphere line. Okay, so in this phase diagram, this is the solid region, this is the liquid region, that's the gaseous region. If the pressure is low enough, you can get a gas at very low temperature. Or if the pressure is high enough, you can go straight from gas to solid at that same temperature. So you can get deposition this way, you can get sublimation this way. So let's look at the choices. I noticed that this one says none of the above statements is correct. So we got to look at all of them. If they're all correct, or let's see, choose the correct statement. If they're all false, then E is right. But if only one of them is correct, then we'll pick that one. The diagram is qualitatively correct for water. Right, what does that mean? Well, that means you need to know something about the phase diagram of water. The water is kind of strange. Most of the time, most substances will go like this, and then they'll go that, and like this. So this will be gas, liquid, and solid. This line between solid and liquid will be positive slope. Okay? Water's different. Water goes negative slope. That. Between liquid and solid. So that's not water. Can't be. The diagram shows that the melting point of the solid increases with increasing pressure. So where's the melting point? Melting point, it depends upon pressure, right? It is the temperature, but it's also pressure dependent. So the melting point is where you go from solid to liquid. Right? So this line increases. In other words, it's a positive slope, which means as the temperature increases, as pressure increases, the melting point increases. That's what positive slope means. Both of them increase together. So the diagram shows that the melting point of the solid increases with pressure. That's true. B is true. How about C? The diagram shows the triple point about 1 atmosphere. Nope. There's the triple point. And it's much less than 1 atmosphere. So C is false. And then D, the diagram could represent the phase diagram of carbon dioxide. Well, let's see. What do we know about carbon dioxide? It sublimes at 1 atmosphere. So if you're at 1 atmosphere, then you should be able to go from solid to gas. Right? Nope, solid to liquid. So 1 atmosphere on the carbon dioxide phase diagram would be down here, where you could go from solid to gas right across that line. So that was probably the trickiest one in the whole bunch, but it's false. That statement is false. So the answer is B for 25. How about 26? Am I going to do 26 also? Yeah, 26. 26 is another phase diagram. So let me scroll down here, 26. There we go. Below is a phase diagram for the compound Q. You wish to purify a sample of Q that was collected at 1 atmosphere and 100 K by subliming it. Okay, so in this case, let's see. I'm going to have to use that diagram. At Greenbrier, we project our stuff on whiteboard. So I can walk up and draw on the diagram, which is convenient sometimes. All right, so if this is the phase diagram for that Q substance, we want to purify it by subliming it. So understand that you can separate Q from other materials if you can sublime it, and the other material will not sublime under those conditions. So in order to sublime the material, we need to go, if it was collected at 1 atmosphere pressure and 100 K, that means it's right here. Okay. Does that show up on the, Elizabeth, does that red dot show up?
Yes.
Okay, good. So if we're starting right here, how are we going to sublime that stuff? Well, we can't increase the temperature because it'll go through, right? And these are not marked. This is gas, this is liquid, and this is solid. So solid needs to skip the liquid. So we can't do it straight across here by increasing the temperature. We could decrease the pressure and then increase the temperature a little bit, and it would sublime. Okay, so let's see. If we decrease the pressure, lower the pressure to 1/2 atmosphere, it'd be right here, then we could increase the temperature. Increase the temperature to 200 K. That would sublime it. That's the same type of process that's used to freeze dry material. The fancy word for it is lyophilize. You freeze dry material. First you freeze it, right? You make all the water solid in your sample, and then you sublime the water from your sample. The advantage to that is by converting water to gas directly, it can pass through cell walls without damaging them. And you also have to freeze it quickly. So that's why when we did it in my research efforts, we would freeze our plant samples in liquid nitrogen. Minus 195 degrees Celsius would freeze instantly. And this funny thing about water, the faster you freeze it, the smaller the crystals. So if you make the crystals smaller than the size of a cell, then they won't rupture the cell walls. So we freeze it fast, and then we put it in a freeze dryer, which creates a vacuum and then adds a little bit of heat. And you sublime the water off, and you've got freeze-dried plant material. The advantage to that is it doesn't alter the secondary metabolites that form in the cell. If you damage a cell, then what you'll do is start this decomposition process. And we didn't want to do that. Okay, so subliming the material here is C, lower the pressure and increase the temperature. Okay, that was 26. Let's see, we're going to skip over 29. There's another phase diagram. 29. Let's see, next one. I'm going to have to scroll a little bit. So as we finish chapter 10, we'll take a short break. And before we go into chapter 11, 29. Okay, here we have a phase diagram that looks to be something like water. Notice that negative slope here between the solid and the liquid. Which of the following statements is false? The solid has a higher density than the liquid. Okay. There's the solid, and there's the liquid. Does it have a higher density than the liquid? Okay, the key here is to understand what this is. This is probably water. And if it is water, that's true. No, that's false. Excuse me, that's false. Solid, normally solid has a higher density than the liquid, but for water, it doesn't. So this statement is false. Based upon this is probably the phase diagram for water. At some constant temperature, right, the gaseous substance can be compressed into a solid and then into a liquid. Okay, the gas can be compressed into a solid and then into a liquid. At a constant temperature, it goes through those phases like that. Okay, that's true. When phase A is compressed at constant temperature at point X, okay, point X, no change is observed. Compressed. Okay, why is that? That's because in this region, you're beyond the critical point. And in that case, you can't tell the difference between liquid and gas. It's just a fluid. So that one's also true. D, when heated at 1 atmosphere, here's 1 atmosphere and you're going to heat it. This substance will first melt, then boil. That's true. All right. So we do have one false statement, and that's A. Simply because we're assuming that this diagram is of water. All right. So let's get over here. All right. Those were the easy section. Now we're going into the moderate section. So I guess I should put a prefix here. Do moderate 1. There we go, moderate 1. Which of the following is correct order of boiling point for, that's chopped off. Let's see if I can. There we go. Which of the following is correct order of boiling point? There we go. Boiling point for potassium nitrate, methanol, ethane, and neon. So the correct order, we have to look at the answers. Okay, we want the boiling point to increase from left to right. Okay, looks like that's the same for each one of them. So the boiling point is going to increase. What I like to do with this type of problem is find the lowest and the highest, and then order the ones in between. So the lowest boiling point is going to be this noble gas, neon. So that means A, C, D are possibilities. Lowest boiling point. And we're going to increase to the right. The highest one is going to be this ionic compound, potassium nitrate. Simply because it's ionic. Okay. So it's going to be on this end. So let's see, neon. Okay, it could be A or it could be D, because there's neon, there's potassium nitrate. What we have to do is decide which one of these is ordered. So look at that. Right. If you know something about the structure of ethane, you have 2 carbons and 3 hydrogens. So it's nonpolar. Whereas methanol is like this, and there's your hydrogen bond potential. So methanol is going to be a higher boiling point than ethane. So that means this one is correct. Lowest, next highest, highest. D is the answer for this one. All right, let's see. What do we want to do? Number 2 also. So let me scroll. Go. 2. Which of the following statements are false? Okay, so we have Roman numeral 1, 2, 3, and 4, and their choices here are 1 only, 2 and 3, 1 and 4, 2, 3, and 4. So let's see which ones of these are false. The layering in a hexagonal closest packed structure is ABA. What is the layering in a closest packed structure? Well, let me see. I need to refresh my memory too. Here we go. Oh, we're looking for false, excuse me. Right. Hexagonal closest packed structure, ABA is correct. So you have one layer, and then you shift B layer over, and then when you put the A layer, the next layer up, it aligns perfectly with the ones below. Remember that video that we watched? The narrator said that he drew lines, and then he kind of shrunk the atoms so you could see the structure a little better. And it was hexagonal. It had like that, and then it had one here, here, and then one up here and one down here. So when you draw your connector lines, you have 4 sides up here, you have 4 sides down here, which makes 8. That's hexagonal. So 1 is true. A body-centered cubic unit cell has 4 atoms per unit cell. A body-centered cubic cell. Okay, there's your cubic cell. You're going to have one here, 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 and here. So you have 2, 4, 6, oops, 8. And then you have one in the middle. Body-centered. How many atoms can be assigned to that unit cell? This one, obviously, right? It's only in that cell, no others. How many others are attached to this one? You got one here, here, here. See. And then you got one out here. You get 1/8 of this one in each one of those cells. So you have 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1/8. So both of them together, you have 2, actually, not 4. Okay. Which one gives you 4? The face-centered cube. Because, excuse me, is that true? Yeah. 1, 2. How many faces do we have here? 6. 6 faces on a cube. Like roll the dice. You have dots on them, 1 through 6. So you have 6 faces, and if you have a face-centered cube, then you have half in this cell and half in that cell. So 6 times a half is 3, plus 1 for the corners, which means 4. So actually, this needs to be a face-centered cube to answer that correctly. 3, for unit cells having the same edge length, a simple cubic structure would have a smaller density than a body-centered structure. Yeah, that's true. Because with a simple cube, all your atoms are touching. Right? These would touch those. All their neighbors, they're touching. So that tends to make the volume smaller. But with a body-centered, it pushes things away, so they're not touching each other. And that decreases the density because you're increasing the volume. All right, so that's true. Atoms in a solid consisting of only one element would have 6 nearest neighbors if the crystal structure were a simple cubic array. Well, yeah. In a solid consisting of only one element, we have 6 nearest neighbors in a simple cube. Right? So get rid of this. Then we have a cube here, cube here, cube here. And then we have a cube up here. That's 3, 4, 5, and 6. So each one of those would be involved with 6 other neighbors. Wait a minute, 6 nearest neighbors. Wait a minute. This one, this one, this one. And then, no, that's right. 3 of these in its unit cell, and then 3 out this way. 3 dimensions. Okay, so the only one that's false here is 2. This one. All right, so I'm going to go to 3. I'm going to take them in order for a while. About 3. What does 3 say? Let's see. Scroll a little bit. Probably get 4 in here also. Yeah. Which of the following substances would you expect to have the lowest boiling point? All right, so we're going back to that. The lowest boiling point is the one that has the weakest intermolecular forces, right? Diamond is definitely a very strong force. Sodium nitrate is ionic. Glycerin or glycerol has hydrogen bonding, and copper has a metallic bond. So really, the weakest, the lowest boiling point would be the gas, methane. It's non-polar and it's a gas at room temperature. So those are the keys. About 4. Assume 12,500 joules of energy is added to 2 moles of water as an ice sample at 0 degrees. Molar heat of fusion is 6.02 kilojoules per mole. Specific heat of liquid water is 4.18 joules per gram per degree C. The molar heat of vaporization is 40.6 kilojoules per mole. The resulting sample contains which of the following? Okay, this is a complex problem that you need to break down. And the best way to do it is to use your phase change diagram. That. So this is your solid, this is your solid liquid, this is your liquid, this is your liquid gas, and this is your gas. Okay. So you've got 12,500 joules of energy to play with. So as you're adding energy in this direction, no, that's time. Excuse me. Time. This is temperature. So as you're adding your energy over time, then the temperature is going to go up. So when you're in these regions, these flat regions, you're talking about heats of fusion and heats of vaporization, right? And remember from our calorimetry class in 101, what's the expression? The oops, not G, Q. Q we're using as standing for heat. So heat then for inside the phase is your specific heat capacity times the mass times the change of temperature. And Q for phase changes is simply the heats of fusion or the heats of vaporization, fusion or vaporization, times change of temperature. So this is going to be units of measure would be joules per gram degree, joules per gram degree C, and this would simply be joules hold on a second. No, the temperature's not changing, right? It's how is the heat of fusion in terms of moles? This is joules per mole, and this is the number of moles. So whether it's fusion or vaporization, it's just number of moles times the value would give you heat. Okay, so if you're starting off with 12,500 joules, what processes are you going through? Well, it says what? Your ice sample at 0 degrees. So you're starting here with pure ice. You're right at that point. So you need to know how much heat is being absorbed for this to be completely melted to liquid. That's your first step. So this is your first step. And your second step is you're going to heat the water, and you're subtracting from the total each time you do that. So what do you have? 2 moles of water. So they're kind, they tell you. So the first heat measurement is this one. The heat of fusion of water is 6.02 kilojoules per mole. 6.02 kilojoules per mole times 2 moles, right? So that's what, 12.04? 04 kilojoules. But that is equal to 12.04 times 10 to the third joules. Or let's make it standard notation here. So let's move the place 3 to the place 3 over or 0. Right, 12,040 joules. Subtracted from that one is what? Right, 0, 6, 4. That's it. 460 joules left over. Okay. So now we're going to heat the water up. So how far can you get with 460 joules? Well, let's see. We need Q, specific heat of water, 4.18 joules per gram degree C, times mass, which is 32 grams of water. 36 grams, excuse me. 36 grams of water. And then our change of temperature. Remember, final minus initial is always delta T. So T final minus, what's T initial? Well, we're still 0 degrees. We're over here now. We're 0 degrees and we're starting to heat it up. So that's minus 0. Okay. So 4.18 times 36. And I'm going to use my calculator in a minute. 4.18 times 36 is 150.5. This right here is 150.5 joules per degree C. And that's times temperature. So this is in the numerator, that's in the denominator, so they'll cancel. So how do you figure that? Well, we need to put this on the other side. So we got let's see. Okay. So this is going to give us TF is equal to 150.5 joules per degree C is the change. And we're going to consume, this is the number of joules we have to play with, so that'll tell us what the temperature is going to be. So we need to divide this into 460. Which is 32.7 degrees. 32.7 degree change. Right. 0 to 32.7 is what? You haven't made it to boiling yet. So what do you got? You're right in here. Nothing but liquid. Only water. Okay. Is that clear as mud? I hope it's clearer than that. That's one of those problems that appears complex, but it can be broken down. And that's the only way to solve complex problems, to break them down into small pieces. These explanations that I'm putting on the board should be here in this handwritten problem solved. Let's see, 4. Right, we are going 5. So let's go down to 5. Which of the following compounds is expected to have the highest boiling point? Okay, we're looking for intermolecular forces, right? So which ones have the lowest intermolecular force? Right? They're all similar in number of carbons. 2, 3, 4 is the maximum. So we're looking for the lowest, of course. Highest boiling point will be the one with the strongest interactions, and we needed something with polar. This is slightly polar. right? Chloroform. This one is nonpolar, and this one's nonpolar. So they only have London dispersion forces available. This one is dimethyl ether. It's nonpolar too. It's very volatile, very low intermolecular forces. If you open a bottle of ether on one side of the room, within seconds you can smell it on the other side. This one is ethanol, the drinking kind. And it has hydrogen bonding available. This polarity is much stronger than this polarity. Chloroform. You can smell chloroform almost as fast as ether when you open the bottle on one side of the room. Not quite. Takes a little longer. But this one is going to have the highest boiling point because of hydrogen bonding. All right, that was 5. Let's see, what am I going to next? Oh. 6. 6 is going to take some effort. It's a complex problem that has to be broken down. Let's see. I'm looking for it in the work problem so that you'll know where to go if you don't get it all copied down from what we're doing. Maybe I didn't work all. Oh, a second. Oh, I'm looking at the wrong page. Here we go. Oh, shoot. Look at chapter 11. Okay. Now we're into chapter 10, difficult. Okay, here we go. All right. So we're in the difficult problems now. Chapter 10. Okay, we're gonna look at number 1. Is that up there? Yep. So you recognize this one as we're firing X-rays at a crystal, and we're looking at the reflected energy, diffraction. And for this, you need the Bragg equation. Okay, and that will be in useful information, but you don't have to memorize it. So we're looking at, let's see, here we go. N times the wavelength, 2 times the distance between the crystal lattices times the sine of the angle. All right. N is the order. Remember when you, if you've ever seen a rainbow in the distance, very often, not always, but often, you'll see 2 rainbows, and one will be the mirror image of the other. The brightest one is first order. but diffraction, depending on where you are in relationship to the interference patterns for the wavelengths, you'll get a second order. So this order number, let's see. First order diffraction is 19.2 degrees. What would be the angle for the second order diffraction? Okay. So what we need is to find out the distance between the lattices, the distance between the layers, because that's not going to change. That will be the same for both instances. Okay. The thing that will change, since this is constant also, right? Since this is constant and that's constant, then these two vary. So this angle will change with the order. So I think the simplest way to solve this one, you can do it two ways. You can solve what is the distance here, right? And then plug that into the other equation. Or you can say, this is going to be equal, this is going to be the same both times, right? 2.33 angstroms, yes. This is going to be the same. This is going to be the same. All right, let's do it stepwise, right? So step number one. First order, and by the way, what's an angstrom? An angstrom is an antiquated unit of measure. Some people still use it. It's actually 10 to the minus 10th meters. So it's a tenth the size of a nanometer. It's just one order of magnitude smaller than a nanometer. And it's useful for short wavelength light beams. So that's where it's most often used. So if we got first order and wavelength is how many angstroms? 2.33. Okay. And then we've got 2 times D, right? We don't know what D is yet. And then we have sine of the angle for the first order, which is 19.2 degrees. So now we just need to solve for that value right there. So if we're going to solve for this one comes over in the denominator, this comes over in the denominator. So if we say, let's solve this one first, 19.2 degrees. Take the sine. So you have to know where your sine is on your calculator. There we go, I got my sine. 0.329 times 2. Okay, now it's going to be over here. I'm going to divide that times that into this. And I get 3.54 angstroms. D equals 3.54 angstroms. Now for step 2, all you need is to modify the equation. So now we're looking at second order. So n is now equal to 2. And the wavelength is still 2.33 angstroms. Right? And we know what D is, but D is going to be over here, right? D is going to be over here. 3.54. And then 2 is also going to be over here. And that's equal to the sine of our new angle. Okay, so first thing we want to do is resolve this one. 2.33 times 2 divided by 3.54 divided by 2. And that's 0.658 equals the sine of theta. So now, how do you get theta out of that? Well, not the inverse, can't say the inverse. The opposite of this, if you were to solve for this theta, On your calculator, you would look for the arc sign of 0.5, 0.658. So the arc sign is usually a function. On mine, you press the function key and the arc sign is just above the sign key. And the arc sign goes backwards. Okay. So all I have to do is kick in the arc sign and I get 41.2. Theta equals 41.2 degrees. Okay. So like I always say, it must be a rounding error. B is 41.1. So if you have all those choices, pick the best one. And the best one is B. Okay. That was number one, difficult. And notice when we solved that problem, for the second one, angstroms canceled. Okay, let's see. This is the second one I have marked off. Number two. Number two. Oh, there it is. We don't have to scroll. Chromium metal crystallizes as a body-centered cubic lattice. Okay. So there's a chromium metal at each of the corners of the cube, plus there's one inside in the body. If the atomic radius of chromium is 1.25 angstroms, what's the density of chromium metal in grams per cubic centimeter? Okay. A lot of chemistry is dimensional analysis. Right? Keep track of your units, know where you're headed. So if we want density, that's where I'd start. Density equals mass divided by volume. And then what mass in grams and volume in cubic centimeters. So what do we need to know? We need to know the volume of that unit cell. Okay? And we need to know what mass of chromium is in that unit cell. So how many atoms does it represent? So there's two separate problems, and then we bring them together here. So what do we say about body-centered cube? Body-centered cube. How many atoms are in a body-centered cube? 2, right? So we have 2 chromium atoms per cube. Okay. So what we want to find out is how much mass does that represent? So that's solving for this part right here. So what do we know? Well, if we convert atoms to moles, then we can use molar mass out of our periodic table. So atoms here and moles here, right? That cancels atoms and leaves us with moles. So what's the magic number? 6.022 times 10 to the 23rd atoms per mole. Avogadro's number. Okay. Now that we know moles, we can convert to grams. We just need the periodic table. So we go to chromium on the periodic table, which I'm off camera now, but it's 52.00 grams per mole. And that's rounded off to 2 decimal places. Okay, so now we know that that cancels. All we got to do is crunch numbers to find out the mass. So let's say 2 atoms, 6.022 exponent 23. Divide that in there and then times 10. So that's 1.727 times 10 to the minus 22 grams. 1.727 times 10 to the minus 22 grams per cell or cube. I should put cell. Okay. Notice I'm hanging on I'm not rounding off yet. Actually, that's only one significant figure. So I'm going to hang on to all those until the end. Actually, this is a counting number, right? It has infinite number of significant figures. And these are conversion factors, so we can keep as many decimals as we want. Right? There's no limitation in this problem. So there's the mass. Now we need volume. Right? So how do we get volume for this unit cell? Well, you need to know how long is the edge of the cell, because the edge cubed is the volume of the cell. All right? So what are we also told? The radius of chromium is 1.25 angstroms. Radius equals 1.25 angstroms. Okay? So we need to find out what's the edge of that cell. Well, in useful information, I'm not going to go back there, but I'm going to flip back to the back. Body-centered cube. That's why I put that one in there. Body-centered cube edge equals 4 times the radius divided by the square root of 3. So the edge is equal 4 times the radius divided by, right? See, I have to look it up too. 4 times the radius, square root of 3. There we go. So that's going to be the edge of the cube. 1.25, and then 4 times that, and then let's see, square root of 3, and then divide it into 2. That's why I like reverse Polish notation. I didn't have to put any parentheses into this thing. Do you understand how it works? Then we've got 2.887. 2.887 angstroms. So that's our cube. We have a cube here, like this. And this edge, A, equals 2.887 angstroms. Okay? Now, we're going to need cubic centimeters, right? So we should convert this to centimeters before we cube it, because whenever you use powers, it kind of muddies the water. So if we convert that to centimeters, then we can cube it, and that'll give us the volume of that cell. So remember what an angstrom is. Let me make the room here. We want to convert this angstrom to cubic centimeters. Well, I don't know off the top of my head the direct conversion from angstrom to cubic centimeters, so I'm making a chained conversion. So we know that angstroms is 10 to the minus 10 meters, right? Now I can convert centimeters. Centimeters, meters, right? So we have 100 centimeters per meter. Now I can crunch numbers and find out what the edge is in centimeters. Let's see, 2.887 and minus 10th, and then 100. So it's 2.887 times 10 to the minus 8. Centimeters on a side. Now we just cube that, and we get the volume. So the volume in cubic centimeters is, see, I've still got it in my calculator, so let me just, let's see, enter, and then here we go. 2.406 times 10 to the minus 23. 2.406 times 10 to the minus 3 cubic centimeters. Is that reasonable? Well, I look at the powers of 10, right? This cubed would be 3 times that, which would be 24. It's in the neighborhood, because this cube is going to give us an extra 1 and bring this back up by 1. So I'm satisfied. by estimation. Now, if we take this value, this many grams, and this many cubic centimeters, and this is per cell, then we divide this one by that one, and that gives us our density. Let's see, if I still got it in my, no, I don't have it. 1.727 minus 22. And then I'm going to flip that. So I get 7.18. Grams per cubic centimeter. Now, let's see. Is that one of our choices? Yep, B. Okay, so that was a multi-step problem. That's probably why I put it in the difficult section, because you have to break it down into pieces. That was number 2. Let's see where we headed here. Oh, that's all the difficult ones I got for you. Okay, that's chapter 10. So we can, if you want to, we can take a short break. If you want to stretch your legs or use the restroom or whatever. 10:20. So that only leaves me 30 minutes for chapter 11, but we don't have a lab, so we're good. And I'm gonna go down to the lab and shut things off because I didn't know what you guys were going to answer, so I kept the water started heating up, and I could turn that off there. All right. Let's see, before I leave, I'll just put the chapter 11 up there.
Always all out, yeah. So, I'm not.
Here we go. Now I'm gonna blow this up some. Oh, that's the wrong application. Let's try this again. Open with. There we go. There. All right. There, we're ready to go. Make myself a note. Do it here. Moving this one down here. So we'll do lab exercise number 1. We'll do it next week. Let's see what's happening in the lecture next week. I think it's the same. That would actually work out pretty good. Yeah, yes, on the 30th. Okay. That's good. Actually works out better. Let's see, that's chapter 10. We'll set that aside. Go to chapter 11. All right. These are the easy group. Number 1, back when we do the whole first page, 1 through 5. They must be basic stuff. All right. In a 0.1 molar solution of sodium chloride in water, which one of the following will be closest to 0.1? What this is getting at is different ways of measuring concentration. Mole fraction versus mass percent versus molality. Which is closest to 0.1 by these other units of measure. So what do we have? We're starting with 0.1 mole, 0.1 molar sodium chloride. So that means 0.1 mole of sodium chloride per liter. Okay. So mole fraction would be what? Mole fraction means that we need to know the total number of moles in our solution, and then the moles of sodium chloride. All right. So we've already got 0.1 moles of sodium chloride. That's good. We need to know the moles of water. So let's see. I'm making an estimation here. Yeah. Yeah, okay, so I'm making an estimation for mole fraction. If we say this many moles, what's the mass of this? Well, in my work problems, I get very particular about the density of the sodium chloride solution. But for estimation purposes, we could say that it's the same as water. 0.1 molar is pretty dilute. I know it's a little bit more dense than pure water. Right? Just think about swimming in the ocean or swimming in the Great Salt Lake. Right? You float higher because it's denser. But if we estimate, then we're going to say that this liter is 1,000 grams. Right? 1 liter is 1,000 milliliters, actually. And then we're going to change that to grams, and it's roughly 1 to 1. So we can say that 0.1 molar is how many moles per gram? It's 0.1 divided by 1,000. So that's 10 to the minus 1 plus 10 to the minus 3 is 10 to the minus 4 mole per gram. And if we assume that there's so little water here, I mean, so little sodium chloride that we can assume this is the molar mass of water, we can change this to the number of moles of solution, which would be, what's the molar mass of water? 16 for oxygen and 2 times 1.02 is 18.02 grams per mole. Okay, so there we have 1.802 times 10 to the minus 3, 10 to the minus 3, let's see. Can't cancel everything now. Oh, excuse me. This is moles of sodium chloride, and this is moles of solution. Because we're going to assume that the solution is virtually all water. So now we have this many moles of sodium chloride per mole of solution, which is the mole fraction. So this is A, mole fraction. That's nowhere near 0.1, right? So how about B, the mass fraction of sodium chloride? In order to do the mass fraction, we need to know 0.1 mole sodium chloride is what mass of sodium chloride? Okay. So if we take this one, 0.1 mole sodium chloride per liter of solution. So this is also one of those cases for dimensional analysis. So we're analyzing this thing with virtually all dimensional analysis. This is going to be mass fraction. This is mass fraction. We need to know the mass of sodium chloride and the mass of the solution. So when you're doing this type of unit conversion, you do one at a time. So we're going to do this one first. 0.1 mole of sodium chloride, we need grams. So we need the molar mass of sodium chloride, which is, I'm going to estimate 23 plus 35 and a half. 23, 35. 58 and a half. Okay. So that means this is going to be 5.85. So got that. Now we need grams of solution. Well, grams of solution is again going to be related to the density of that solution. So we're going to assume that it's basically water. So for 1 liter of water is a kilogram. So 1 liter is 1 kilogram, and then we change that to grams. There we go. So we got rid of liters, and this kilogram cancels that kilogram. So this is grams of solution, and this is grams of sodium chloride. So we're only going to calculate numerator, and then we'll calculate denominator separately. So, this is 5.85 grams of sodium chloride per 1,000 grams of solution. Okay, so that's 1,000 into this would be 1, 2, 3. 0.00585 mass fraction. So that's nowhere near 0.1. How about C, mass percent? Right. Well, what is percent? It's this divided by that times 100. Right. This is mass fraction. So times 100 would be mass percent, which is equal to, let's see, 0.585 mass percent. And that's C, right? So that's not 0.1. Let's see. How about what's the last one? Molality. Yeah. Molality. Yeah, the molality. So D is molality. Well, we can actually, we've already proven that none of these are close to it. So by process of elimination, molality should be close. But we can reason it because if 100 milliliters is, if we're estimating the mass of the solution, it's about 1,000 grams, which is 1 kilogram. 1 liter is 1 kilogram. So if we say 1 liter is 1 kilogram, it's still 1 into 1. So this one for D, the molality is very close to 0.1 molality. So molarity and molality are very close to one another. The difference, the main difference is that this one changes with temperature, this one does not. All right, that was number 1. Now number 2. Too easy. Let's see. Yep, it's all on the board, so we can go ahead on. Which of the following concentration measures will change in value as the temperature of the solution changes? I just told you that, right? Which one does not change? Molality. So which of the following concentration measures will change? Right? Molality won't change. Mole fraction won't change either, because the number of moles, I mean, temperature has no effect on the amount of something. It has no effect on mass. It has no effect on moles. So mass percent is stable. Mole percent is stable. Molality is stable with temperature. Molarity is not, because it's ratioed with volume. And volume changes with temperature. Some solutions change a lot with temperature change, so minor temperature change. Some of them very little. So the answer is D to number 2. How about number 3? I'm pretty sure that's on the agenda. I can get 5 snuck in there. There we go. So 3. Which of the following chemical or physical changes is an endothermic process? Endothermic requires heat. You have to put energy into it in order to make the process go. The evaporation of water, yep, that's endothermic. You're changing from a liquid to a gas. You have to add energy to get those molecules apart. Combustion of gasoline, that's definitely exothermic. If it were not exothermic, we wouldn't be able to drive our cars. The mixing of sulfuric acid and water. If you've ever mixed concentrated sulfuric acid in water, it gets hot, and I mean very hot. That's why the safety rule of thumb is do as you ought to add acid to water. You add acid to the water because the heat of solution for acid in water is so high that a very little amount of acid added to water makes a little heat, and a lot of water absorbs that heat efficiently. If you add water to acid, then the heat of solution is going to be high enough to boil that water, and it'll spatter in your face. So you add the concentrated sulfuric acid, do that for bases too, add them to water. So that's exothermic, freezing of water. So we're going from liquid to solid. In other words, from less stable to more stable, we give up energy to do that. So this is exothermic also. The only endothermic process is this one, evaporation of water. And I think 4 is next. Which statement above about hydrogen bonding is true? All right, let's take a look at our choices. All right, they're all unique answers. So we got to pick one. Only one of them can be true. Hydrogen bonding is intermolecular attractive force between two hydrogen atoms. Nope, don't think so. You got to have a very electronegative atom attached to a hydrogen in a molecule, which produces that uneven distribution. So something over here draws electrons to itself and gives you that negative here, positive there. Okay, that X could be nitrogen, oxygen, fluorine, sometimes sulfur. Most often oxygen and fluorine. They're very electronegative. So A is false. B, the hydrogen bonding capacity of water molecules cause this molecule, which is butane, I think, yeah, butane, to be more soluble in water than methanol. No, butane is hydrophobic. It is nonpolar. It does not dissolve in water, whereas methanol has the potential for hydrogen bonding. So if it had said methanol here and butane here, it would have been correct, but no, B is false. Hydrogen bonding of a solvent molecule of solvent molecules with a solute will not affect the solubility of the solute. Well, that's just ludicrous. Hydrogen bonding is effective for dissolving solute molecules if there is hydrogen bonding available. So methanol and ethanol are very soluble in water. Any ionic compound is very soluble in water. And most polar molecules are soluble in water. Hydrogen bonding interactions between molecules are stronger than the covalent bonds within molecules. No. The covalent bond itself is the strongest bond as a general class. All you have to do is think about what would happen if the energy you put into a solution were sufficient to break covalent bonds. Then you'd have some pretty interesting chemistry going on there. Like you could break the bonds with water, you just heat it up. So the intermolecular forces are always weaker than the intramolecular forces, the forces holding molecules together. E, hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons with certain covalent bonds within a molecule. That's true. That is the only true statement in this list of 5. Okay, speaking of 5. Yep, we're going to do 5 also. Which of the following favors the solubility of an ionic solid in a liquid solvent? About a large magnitude of the solvation energy of the ions. So what do we mean by that? Let's see, did I put a description in number 11? Fine. No, I pointed you to section 11.2 in Zumba in the textbook. So let's see if we can reason this out. We've got all of the above or none of the above. Which of the following favors the solubility of an ionic solid in liquid solvent? So we've got an ionic solid, like, for example, sodium chloride, and we want to put it into a solvent of some kind. Now, what's the nature of that solvent? Okay. Which of the following favors the solubility? Okay, so it's an open question from now on. A large magnitude of the solvation energy of the ions. All right. Let's look at what happens when a solution is made, right? Remember this three-step process? Step one, break the solute, break solute bonds. Whatever is holding the solute molecules together, or ions together, so we've got to break these bonds. This is endothermic. You got to put energy in. The second is, it's often described as make a hole. Break the solvent molecules apart. Break solvent bonds. And these bonds are intermolecular. You don't need to split the solvent molecules apart. You want to move the solvent molecules apart so that you got space for your solute. This is endothermic. Then the third step, you form bonds. Solvent with solute. And this is exothermic. Okay, those are the three-step process. All right, so let's look at our choices. Large magnitude of solvation energy. Solvation energy is here. This is solvation. Well, actually, solvation energy incorporates all three. We don't separate the steps for solvation energy. Is that correct? If this were correct, and it were large magnitude of solvation energy, that means you have to put a lot of energy in here, a lot of here, and you get a little back. So large solvation energy would not favor dissolution because you get nothing back. You got to put a lot of energy in and you get nothing back. So A is false. A small magnitude of the lattice energy of the solute. Okay, what's the lattice energy? Lattice energy is when you, I put it on the board a little earlier, but I didn't call it lattice energy. So lattice energy is the energy that's given up, it's exothermic, when, let's use sodium chloride as an example. This sodium ion as a gas plus chloride ion as a gas yields sodium chloride solid. So this will be exothermic if it goes this way, but when you're going this way, when you're breaking it apart, you have to go the other direction. It's extreme endothermic. So if it has large lattice energy, that means you got to put a lot of energy in here to break it apart. That does not favor dissolution. Excuse me, small magnitude of lattice energy. small magnitude means you get a little energy back. Oh, it's easy to break them apart, excuse me. Lattice energy, small lattice energy. That's possible. Actually, that would favor. Actually, large magnitude of solvation energy. If you get a lot of energy back in solvation, that does favor dissolution. Okay, I misspoke. If you get a lot of energy back from the process, then that means it takes a little energy here, a little energy here, to get a lot back. Large magnitude solvation energy. That's true, right? That is true. Small lattice energy takes very little energy to break these apart. That also favors dissolution. Large polarity of the solvent, definitely. If you've got a polar solvent and ions, they're going to interact very intimately here. Right. So all three of those work. Yeah, all three of them favor the formation of solution. Each one of these is true, true, true. All of the above. Did I confuse anybody there? I almost confused myself. That was number 5. Let's see, where do we go next? Page 6, 7, 8. Knock all three up here. Let's see if I can move it down, catch all 6. Just 6 and 7. Like now I have to scroll to get 7. Well, let's focus on 6. All right. 6 takes some doing. And actually, I'm not sure why 6 is under easy. 6 is at best would be moderate. And at worst would be difficult. So what is it asking for? Solid potassium fluoride has a lattice energy of minus 804 kilojoules per mole. So solid KF has a lattice energy of minus 804 kilojoules. So what does that mean? The lattice energy is, like I said before, lattice energy is potassium gas plus fluorine gas yields potassium fluoride solid. And the delta H for that is minus 804 kilojoules per mole. Okay, let's see that. Kilojoules per mole. Okay, the heat of solvation in water with a heat of solvation of minus 15 kilojoules per mole. Let's see. I want to be sure I don't tell you wrong. Okay, heat of solution says heat of solution is minus 15 kilojoules per mole. So what's the heat of solution? Well, what we're saying is that KF solid to K aqueous plus F aqueous. That's the heat of solution. And that delta H is minus 15 kilojoules per mole. Okay, so that's Kf. Now we're comparing that with rubidium fluoride, and that is in the same group as potassium. It's just one below it. So the lattice energy for rubidium fluoride gas plus chlorine gas rubidium fluoride solid. That delta H is equal to minus 768 kilojoules per mole. And the heat of solution here, rubidium fluoride solid to rubidium aqueous plus fluoride aqueous is minus 24 kilojoules. That's everything that's given in this problem. So the question is, which salt forms the stronger attraction with water? So what are we asking for? Which one forms a stronger attraction is, okay, we look at our three-step process. So let me see if I can squeeze it in up here. A three-step process. The total heat of solution is three steps. You got to put energy in, which is the delta H of lattice energy. Okay. Then you got to put energy into the heat of, let's see, what did I call it? Solvent expansion. Delta H for a solvent expansion. Okay. So here we're making a hole. Here we're busting apart. And this is the interaction of the solvent and solute that I'm calling solvation, delta H of solvation. So there's our three-step process. Now, how does this help us answer the question? The question is, which salt forms a stronger attraction with water? The stronger attraction with water is this delta H of solvation. Right? Okay, that delta H of solvation, we want to find out which one gives up more energy. We know this one gives up more energy, but this one is a negative input of energy. No, positive. Input of energy, this one gives up energy, negative. But this is going to be the same for both of them. Right? Solvent expansion for water is the same. Oh, so we can look at it this way, and this is a single value. If we compare this value for one with the value for the other one, then we can say something about which one is a stronger attractor. We need to find out what this one is. So we have a value here for minus 804. So we've got to put energy in, and the heat of solution here, right? This is look at this. Okay, this is important. This value is for these coming together to form that solid. In order to break it apart, we need a positive input. Right? So that's going to be a positive value. So for the Kf, the delta H of solution, and this is actually a negative number, the delta H of solution here is minus 15. Minus 15 kilojoules per mole is equal to a positive 804 kilojoules per mole. For the lattice, actually, it's the lattice energy in reverse. And then plus, and this is, what are we going to call that delta H? It's a combination. Delta H of hydration, we should say. Delta H of hydration. So delta H here is going to be a negative 819 kilojoules per mole. For this one. For rubidium, and my markers get weak. Give it a rest. For rubidium, we have what? Minus 24. Minus 24 kilojoules per mole equals what? Minus 768, but it's a plus 768. Plus delta H of hydration. Okay. So this minus 768 minus 24, 768 and 24 is minus 792. Minus 792 kilojoules per mole equals delta H of hydration for rubidium fluoride. This one is here. This one is here. Now, what does that mean? Well, it's a release of energy, correct? Negative value is a release of energy. So which one has a stronger attraction? The one that gives up more energy when it solvates, or when it hydrates. So this one would give up more energy than this one. So KF should have a stronger attraction. Let's see. Yeah. Let's see. Here. KF, since it has a more negative heat of hydration, the KF has a stronger attraction for the solvent. Okay. I danced around the barn several times to do that one, but that's because I was trying to explain every step of the way. It all goes back to this relationship. And 6. Ooh. That marker doesn't want to come off. My marker works better than your marker. I brought these markers from home, bought them myself. Better quality. Okay. Let's see, 6, 7. Okay, let's look at 7. I need to scroll a little bit. There we go. All right. Okay, I don't know why I did that. 6 should have been in the moderate category. 7 is still in the easy category. Okay. Use the following drawing of gaseous solute in equilibrium with a solution to help answer the question. Which of the following statements are true when the piston is pushed downward? All right, so when we push down, we've got a gaseous solute. Think pop. You're dissolving carbon dioxide in the liquid, in the syrup or whatever of your pop. So, and the controlling law for that is Henry's law. So the solubility of that gas is going to be equal to some constant times the pressure. So as the pressure increases, solubility will increase. This is Henry's law. I may not have written it exactly the way it's written in the book, which is probably a no-no. I should be consistent. Let's see. Okay. Solubility. We expressed it earlier. Concentration in solution is proportional to pressure over the solution. So the solute is a gas and the solvent is a liquid. And if you increase the pressure, you get a higher concentration. That's almost intuitive. Now for the problem. Which of the following statements are true when a piston is pushed down? Right? So when you push that piston down, you're going to increase the pressure over the solution. Right? That's Boyle's law. Pressure and volume are inversely related. So you decrease the volume, you increase the pressure. So we're increasing the pressure over that solution. Now what? This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go down. False. Concentration will actually go up. They're directly proportional. Pressure goes up, concentration goes up. B, this will cause the pressure of the gas to decrease and the concentration of the dissolved gas to go down. Wrong, right? Both of those statements are wrong. The pressure of the gas will increase quite a bit in the beginning, and then remember Le Chatelier? System was at equilibrium before. We're going to disturb the system. We're going to increase the pressure. So how does the system respond? It tries to absorb some of that pressure. And it does so by dissolving the gas in the liquid. So we're combining Henry's law and Le Chatelier's principle. That makes B false. Can't be. How about C? This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go up. That is a true statement. Now, do we have any other competing statements here? No. We don't have any that say none of the above, all the above, one of the, two of the above, those weirdos. So we can stop here. If you're in the middle of a test, you got the right answer right there. D, this will cause the volume of the gas to decrease. Well, yeah. And the concentration of the dissolved gas to go down. False. Concentration goes up. This will cause the volume of the gas to increase. No. You can stop there. Okay. So C is the answer for 7. All right. Did we do Le Chatelier's principle in the first semester? I have to keep checking. I think so. Hold on. Satisfy my mind. No, we haven't done the Chatelier's principle. Sorry. I referenced a law that we haven't discussed yet. But you got a taste of it anyway. Okay. We're going to move on to 8. All right. Let's see if I got a fresh one here. All right. I hope this is fresh. Yeah, that's good. Okay. Which of the following correctly states the relationship between temperature and the solubility of a substance in water? Well, now they say substance. They don't say what phase it is at normal room temperature and pressure. So it could be a solid, liquid, or gas. So we know that gases respond differently to temperature and solubility than do liquids and or solids. So we have to keep that in mind as we read our statements. The solubility of a substance in water increases as the temperature rises, especially for gases. That's the key. Solubility of a gas in water decreases with temperature. As you increase the temperature, the solubility decreases. Proof of that, practical. If you have a bottle of pop and you open it at room temperature, what do you get? You get a loud pop. They don't call it pop for nothing. If you stick it in the refrigerator for several hours and let it get cold, then you crack the top. You get just a fizz, a hiss. There's more of that gas dissolved in the liquid at a lower temperature. So that's why this one is false. Solubility in water decreases for gas as the temperature increases. That's why before I open a bottle of pop, I always put it in the refrigerator first. That's why I hate going to picnics most of the time, because they got these hot bottles of pop sitting out on the picnic table. And as soon as you open that thing, you lose half your carbonation because it's at a high temperature. The solubility of a substance in water decreases as the temperature rises, especially for ionic solids. That's just the opposite. For solids, ionic solids, the solubility increases with temperature for most ionic solids. There are a few exceptions. But this general statement, decreases as temperature rises for ionic solids, is a false statement. The solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. That is true. There are some ionic solids that are less soluble as the temperature increases. There are a couple of the sulfates that come to mind. They're less soluble. So C is true. So this one says both A and D are correct. Can't be, because C is true and it's not included. So we look at D, the solubility of a substance in water decreases as the temperature lowers, especially for gases. It's the other way around. Decrease the temperature, gases become more soluble. All right, so that's number 8. Let's see. Skip 9, go to 10. Okay. A solution contains 1 mole of liquid A and 3 moles of liquid B. Okay. Now we're talking Rayo's law, where you have the temperature, pressure, vapor pressure relationship of a liquid. So you have the pure Rayo's law says that the solute is not volatile. It's like sodium chloride dissolved in water. Right. So the pure Rayo's law is the vapor pressure of the solvent, the actual vapor pressure, is related to the pure solvent. Right. This is 100% and this is a fraction. We need to know the mole fraction of the solvent to make that calculation. So the mole fraction of the solvent is always less than 1, or it's 1 or less. If it's 1, they're equal, of course. But if there's a mole, if there's any solute in the solution, then this value is going to be less than 1. So that means the pressure of the solvent, actual pressure, actually this, I should say, solution. There. The vapor pressure of the solution is less than the pure solvent based upon the mole fraction of the solvent. Okay, but in this case, let's see, we have 1 mole of A and 3 moles of B. This solution has a vapor pressure of 314. Liquid A has a vapor pressure of 265. B, okay, this is a modified Raoult's law because both the solvent and the solute are volatile. So we have to modify this one. So the total pressure is equal to the partial pressure of A plus the partial pressure of B. And you would have this type of relationship for each one. So as the mole fraction of A increases, the mole fraction of B decreases. And remember that diagram here. So this is vapor pressure. And this direction, the mole fraction of A is increasing. And this way, the mole fraction of B is increasing. So if the mole fraction, if it's pure B, then it'll have a certain pressure. And if there's no B, then it will, let's see. Well, if there's no B, it won't have any pressure. But for A, if there's no A here, so this is 0A and this is 0B, then it will have its own vapor pressure with its fraction. So as its fraction increases, it will be, let's go up here. Wait a minute, let's be consistent. Okay, pure A has 265 torr, pure B is 355. So pure B is 355, pure B is 265, so it's going to be down here somewhere. Right? Liquid B has a vapor pressure of 355. So pure B is this one, and pure A is that one. So this one will rise to there if they're just pure solvent, and this one will be up here like this. So the combination is the sum of these two. So you get a line between here and here. Right? So this is A plus B at the various mole fractions. This is ideal. If this line is straight, then these two components, A and B, behave independently of one another. Okay, so now we have, what is that? That's in torr, which is millimeters of mercury, 355. Okay, so now this solution has a vapor pressure of 314 at 25 degrees C. Okay, which of the following is true? If we I want to say this right, that's why I'm hesitating. What would be the expected pressure? The expected pressure would be, add those two together. Well, actually, this is not true. This is at some, let's see, the solution at 25 degrees, these two mixed together individually have vapor pressure. So that's really not true. This is what we want to look at. So A is 265. A is 265. And B is 355. Okay. But this would be ideal. It's just that we're somewhere along here. We're not actually out here, pure. It's in here somewhere. We want to add this one to this one, gives us that one. So these two together, we would expect the ideal pressure to be 624, right? 5, 5, 11, 12, wait, yeah, 622. If that were true, then they would be right on this line. But what is the actual measured pressure? Let's see. 314. So the actual measured pressure is 314. This is expected. This is actual. Now that I got my story straight, this is less than that. So what does that mean inside the solution? What's going on at the microscopic level? These components are attracting one another. Right? What they're doing is they're causing neither one of them to vaporize as efficiently as they would if they were pure. Right? So there's a strong attraction between the two, keeping them from vaporizing. So with that in mind, let's see what the statements say. This solution exhibits a positive deviation. No, it's a negative deviation from Rayo's. If we're expecting it here, it's less than we expect. So B, this solution exhibits a negative deviation from Rayo's law. That's true. This solution is ideal? No. More information is needed? No, we got enough information. None of these is true. Well, one is true, right? This solution exhibits a negative deviation from Rayo's law. Simply because of this. This would be ideal. This is actual. So we have a negative deviation. So what would it look on this curve? It would be like this. It would be concave. And in there somewhere, probably in here somewhere, right? We expect 620 there, and we get 314 here. All right. That's 10. We can go to 12. How are we doing on time? I'm up on 11:30. Oh, we're good. Number 12 then. Let's just move it up a little higher. A cucumber is placed in a concentrated salt solution. Have you ever done that? Maybe not a cucumber. Maybe a potato, we put it in a salt solution. What happens to it? It gets limp, doesn't it? Yeah. This is referencing osmotic pressure. So if you put a cucumber in a concentrated salt solution, what will most likely happen? Which way will water flow? Well, water is going to flow, and we're assuming that the cell membranes of the cucumber act like semi-permeable membranes. Water can go in, water can go out. Which way is water going? Water is going from the high concentration of water to the low concentration of water. So if the cucumber cell is here, and this is high sodium chloride, what's inside? Low sodium chloride, or low salt solution. So water is going to move that way. It's going to move to the high concentration salt solution. And that's why it gets limp. The cucumber just, it's kind of like rubber. Which one matches that? Water will flow from the cucumber to the solution. That's true. No change, false. Salt will precipitate, false. Salt will flow into the cucumber, false. Water will flow from the solution to the cucumber, false. So A is the only one that satisfies those conditions. That was 12. That was easy. How about 13? I think that one's been used before. Let me get a fresh one. Yeah. Here. Need to prime it. I did that one time with the cap off. It threw ink everywhere. Never did that again. Okay, 12, 13. Okay, more slingies. There we go. Now start to right. Osmotic pressure depends on all but which of the following. Okay, this goes back to the definition of osmotic pressure. And we need the formula. Osmotic pressure is given the capital pi equals molarity, moles per liter, times the gas constant times temperature. And the temperature in this case, let's see. K, that's right. Temperature is in K because the gas constant's in K. And this one's going to be, the gas constant here is going to be the old familiar. Liter, atmospheres, mole, K. That's this one right here. We know that because molarity is moles per liter. So liters per mole will cancel molarity. And K will cancel temperature. We're left with atmospheres. And pi is measured in atmospheres. This is osmotic pressure. So which does it depend upon? All the following except. So it depends on temperature, it depends on moles, and it depends on volume. So let's see, there's temperature, it depends on that one. The molarity of the solution, okay, it depends on that one. The ratio of moles of solute to solution volume, which is the same thing as molarity. And atmospheric pressure, it does not depend on. It is independent of atmospheric pressure. All right. Let's see. I got one more easy and then we move into moderate. So 14. Scroll down a little bit. Yeah, there's 14. Shaving cream is an example of which colloid type. Remember the different types of colloid. Let's look at it. A, B, C, D, E. A is an aerosol. So an aerosol includes either a liquid or a solid in a gas, suspended in a gas. A foam could be a gas, well, it's a gas in a liquid. It's a foam. Emulsion. Emulsion. Think liquid in a liquid. Think mayonnaise is an emulsion. So you put, what do you put in there? Vinegar, egg white, water, and oil. So the oil is a liquid in water and vinegar is the dispersing medium. We can't say solvent or solute because these are not solutions. So it's dispersed in a dispersing medium. And D, sol. So a sol is a solid in a liquid. And then E is coagulant. right? That's not an emulsion. I mean, it's not a colloid. Right? That's what you do to a colloid when you want to separate it. You coagulate the dispersed medium. So shaving cream is what kind? It's a foam, a gas, and a liquid. Now the shading gels, right? Shading gels, they have a mixture of, at first it's a liquid in a liquid, right? So the shading gel is an emulsion, but the dispersed medium is a liquid with high vapor pressure at room temperature, at body temperature actually, because it doesn't start foaming really good until you put it on your skin in that heat. So this liquid, the materials they often use for this dispersed medium are hydrocarbons like let's see, isopentane is one common one I've seen. Isopentane. Pentane is like this, 2, 3, 4, 5. And it's got hydrogens all around. It's a hydrocarbon pentane. Isopentane takes one of these carbons and puts it over here, either here or here, and it doesn't matter. Whichever one. This one is like the mirror image of the other one. Right? So what that does is it decreases the boiling point of this compound over that one. So it's low enough boiling point, so when you put it on your skin, your body provides enough heat to vaporize it like that. And that's why it goes from whatever color, blue or pink. I think women's shave cream is pink and men's blue, something like that. It starts to foam because this stuff vaporizes. And then it becomes a foam when it started out as an emulsion. They use some other compounds like isobutane. They wouldn't use propane. So that's the most common one, isopentane. It's probably cheap too. Okay. So let's move on. I can put a number on that. That was number 14. We're going to skip 15 and go to moderates. Moderates, we're going to do 4 and 5 together, moderates. I think I put this review document together before I had a clear idea of how I wanted to number them. So that's why it's divided this way. 4 and 5. Okay, 5's on the next page. So we'll do 4, and then we'll go to 5. I think 5 uses the same arrangement. Yeah, it does. Okay. 4, and we have our selection here. And E. Okay. So which of the solutions, 0.1 molal sodium chloride, 0.15 molal glucose, and 0.1 molal calcium chloride would have what? The highest vapor pressure, the lowest boiling point. Okay. So out of those 3, 0.1 molal sodium chloride, 0.15 molal glucose, and 0.1 molal calcium chloride. Okay. The key first here is to introduce the oh shoot, painted myself into a corner. Van Hoff. I knew it'd come to me. The Van Hoff correction factor. So ideally speaking, the colligative property would be determined not by this concentration, but by the concentration of the ions in solution. All right. So this would be equivalent to 0.2 molal ions. Glucose doesn't dissociate. All right. So it's 0.15 molal, whatever. Calcium chloride dissociates 1, 2, 3 ions. So it's 0.3 molal ions. So now we have comparison of this one, and this one. Now we can look at vapor pressure, boiling point. So we want the highest vapor pressure, lowest boiling point. Highest vapor pressure, lowest boiling point. All right. Highest vapor pressure means the lowest, and these are all non-volatiles. Right? So Reynolds law says for these, the unmodified Reynolds law says as we increase these amounts, the vapor pressure will go down. So the lowest vapor pressure would be highest vapor pressure, excuse me. The highest vapor pressure will be the lowest concentration of solvent. This one. So 0.15 molar glucose is the highest vapor pressure because it has the lowest concentration of solvent. And then the lowest boiling point. The lowest boiling point is the colligative property for delta T boiling point equals the boiling point constant times the molality times the change in temperature, times concentration. This is specific to the solvent. That's it. This is boiling point elevation. So the higher the concentration, the higher the boiling point. So we want the lowest boiling point, we want the lowest concentration. So the lowest concentration, this is one of the colligative properties. The lowest concentration will give you the lowest change in boiling point. So again, we want this one. Molal glucose. So that's why the answer is D. Both this one for each one. Highest vapor pressure, lowest boiling point. Okay, so now let's see, can I do this? Yeah, there we go. So now we're going to look at the lowest vapor pressure. So this is going to be 5. I don't even need these. Using the same set of information. Now we want the lowest vapor pressure. And the lowest boiling point. So the lowest boiling point is again going to be, just like before, molal glucose. The lowest vapor pressure will be the one with the highest concentration of solute, which will be this. 0.1 molal calcium chloride. Okay. And we skip moderate. No, that was moderate. Oh, let's get number 3. Yeah, let's go back to 3. And let me scroll. There we go. I skipped this one. Backtrack. This is moderate. And so I've been in the moderate zone, calling it easy. Okay, so for this one, 0.2 molar solution of solute X. 0.2 molar X in benzene. Okay. Displays an osmotic pressure given by the formula, 0.1 RT. 0.1 RT. Okay, what does this mean? Well, this is where molar is supposed to be. But we've introduced a correction factor. And the correction factor was 1. It was actually 1/10. No, excuse me, it was 1/2. So it would be like this, 1/2 M is equal to this. So this is our correction factor I, right? The Van Hoff correction factor. We normally think of it as a positive number because we get dissociation of ionizing or ionized compounds. But in this case, what happens? Well, when we put X into solution, we get X forming bonds with benzene. No, excuse me. No, we don't. We get X forming bonds with itself. So out here it's X, but in solution, it forms bonds with X and X. So that decreases the number of X's by 1/2. So which one explains that best? X exists in benzene as X? No. X exists in benzene as X2. That's true. It forms this association in solution that it doesn't have out here when we measure it. Okay? That's kind of tricky. Because we normally think of the Van Hoff as a whole number. Okay, I think we're headed for difficults and then we're done with chapter 11. Yeah. Okay, how many difficults do we have? 1, 2. I picked out 2 difficults out of the available. Let me scroll down to the difficult zone. Here we go. There. A solution is prepared from 53.8 grams of a non-volatile, non-dissociating solute and 85 grams of water. The vapor pressure of the solution is 60 degrees Celsius. Oh, the vapor pressure at 60 degrees is 132 torr. The vapor pressure of water at 60 degrees is 150 torr. What's the molar mass of the solution? Okay. This is a complex problem. That's why it's in the difficult zone. What you have to do is read the problem backwards. What's the molar mass of the solute? What do we need? What information do you need to answer molar mass? So I'm old school. Molar mass for me is molecular weight. Molecular weight is the mass per mole. You have so many moles, and that many moles has that mass. Okay, so that's the information you need. You need mass and moles. All right, how about mass? Solution is prepared from 53.8 grams of non-volatile solute. 53.8. We got it already. Now we got to find out how many moles does that represent. What's the colligative property that we're investigating here? The vapor pressure of the solution. Vapor pressure of the solution is 132. The vapor pressure of water is 150. All right. So now we're going to look at, let's see. I'm doing this just to save myself some time. Okay. We're going to use Rayleigh law. That means the vapor pressure of the solution equals the mole fraction of water times the vapor pressure of pure water, mole fraction of water. So we know the vapor pressure of the solution, correct? 132 torr. We don't know the mole fraction of water. If we find the mole fraction of water, is that going to tell us the mole fraction of the solute? Yeah, because we've only got two components. So if we know the mole fraction of water, 1 minus that is the mole fraction of the other one. So what's the pure? Pure is 150. So the amount of solute in here has changed from 150 to 132. So the mole fraction of water is equal to 132 divided by 150. Zero 0.88. 0.88. So the mole fraction of the solute is equal to 1 minus 0.88, or 0.12 mole fraction. Okay. So that tells us the mole fraction, but it doesn't tell us how many moles. So what we need is how many moles of water are there? 85 grams. We know the moles of water, then the mole fraction of water equals the moles of water over the moles of water plus the moles of solute. We may not even need this number. This might tell us also. If we know this one, we need the moles of water here, and then we'll solve for this one, the moles of the solute, right? So we don't need this one. So how many moles of water do we have? 85 grams of water. Let's convert that to moles. That's 18.02 grams per mole. Right? 16 for oxygen and 2.02 for the hydrogens. So 85 and 18.02. 4.717. 4.717 moles of water. Okay, now we can find this, because that will fit right here. Right? So what's this one? 0.88 equals
4.717 divided by 4.717 plus, let's just call it X for now. Now that's too easy to get confused with the other one. Let's just call it moles. Okay, so we move this one over here, multiply 0.88 times both of those. Let's see. 0.88 would be 4.151. 4.151. This one times that one, and then we have 0.88 n equals 4.717. So 0.88 n equals this one minus that one, which is 0.566. And then the number of moles is this one divided by that one, which is 0.643. Now, this is equal to 0.643 moles. So we just divide that into 53.8. We got 83.6 grams per mole. And it's this one right here. Okay. Remember in Chem 101, first semester, we were learning how to determine empirical formula and then molecular formula from two different sources of data. The empirical formula was mass percent. If you know mass percent of the elements, you can find empirical formula pretty quick. But in order to convert empirical formula to molecular formula, you need the true molar mass of the compound. This is one of the ways to get it, because we don't know what the compound is, right? We have no idea. We use colligative properties to give us the molar mass. And then we combine it with empirical formula to give us the molecular formula. Now, that may not tell us everything we need to know, but we're one step closer. Other ways, this way we use Rayleigh law, right? That's one way to get the true molar mass. You can use osmotic pressure. It's a colligative property. You can use boiling point boiling point increase, or you can use freezing point decrease, right? And that's what we're going to use freezing point decrease next week to determine the molar mass of benzene. And we probably ought to talk about that a little bit, assuming I don't take up all the time in review. Let's see, I have one more that I want to do. Yeah, I have one more. And then we can talk about the lab for next week. Okay, let's see. 4. Here it is. This is difficult. I should have erased that part. 4. You have a 10.40 gram mixture of table sugar and table salt. So we don't know what the composition is. We just know that both of them mixed together would give us 10.4 grams of that mixture. When the mixture is dissolved in 150 grams of water, the freezing point is found to be minus 2.24 degrees Celsius. What's the percent by mass of sugar in the original mixture? All right, so let's say percent by mass of sugar. So we need the mass of sugar divided by the total mass times 100. That's what we're aiming at. What are we given? Well, we're given 10.4 grams, 10.40 grams of sugar plus sodium chloride, is it? Yeah. the mixture is dissolved in 150 grams of water. So 150 grams of water solvent. Okay. I like to, especially on word problems, I like to extract the information from the word problem because word problems are designed to confuse. So if you pull the information out of it and then ask the question, or ask the question first and then pull the information out, then lots of times it becomes clearer as to what you need to do to get the answer. The freezing point is found to be minus 2.24. So the freezing point of this solution is minus 2.24 degrees Celsius. Okay. And we're looking for the mass percent. That's the question. All right. So how do we approach this problem? Well, if we're told that this mixture depressed the freezing point, we're definitely going to be working with the freezing point depression. Is equal to the K for freezing point times the molality of the solution. So we know that. So we've got this value and this value we have to be given. We have to look it up. So let's see, is it in useful information? Let me see. It's in constants. Let's see. Well, there's some constants. There it is at the bottom of the page. KF. Yeah, KF for water is 1.86 degrees C kilogram mole. 1.86 degrees C kilogram mole. That's K. So if we, and remember when we're using this equation, this change in temperature, we know it's a freezing point depression. You leave the sign off. It's actually absolute. So this would be 2.24 degrees C is equal to that times the molality. So we can find the molality of this solution in combination of these two. So what's the, I wish they'd chosen a different symbol for molality because we think it's mass. It's not. Let's try to be clear here. This is mass. Let's see. Let's get where I was for. All right. The problem here is that this dissociates and this doesn't. Right. So the molality here for one is going to be different than the molality for the other. So that's the real trick to this problem. All right, here we go. The change in temperature is actually due to the linear combination of the two solutes. So this delta T is going to be equal to the K for water times the molality of sugar. Right? We don't, yeah, the correction factor is 1, so we don't have to worry about that. And then the linear combination then of K is the same freezing point depression constant for water for either one. And this one has 2 here, sodium chloride. And this is molality of sodium chloride. Okay.
So that's the tricky part of this entire operation, recognizing that those two have to be incorporated that way. All right. So we have point. Let's see. Moles of sugar. Okay, so if you take this one down and expand it, I'm gonna leave the freezing point off here. This is moles of sugar divided by the mass of the solvent in kilograms, 0.150. Okay, and this is the same K, and then 2 times the moles of sodium chloride divided by 0.15 kilograms. There we go. Okay. So we also need to recognize that, let's see, where was it? Here it is. Yeah. We're headed for this relationship, mass of sugar. So let's let the mass of the sugar be equal to X. X equals mass of sugar. Okay. And now we can fill in some values here. The change in temperature is 2.24 degrees C. The K is 1.86. And if we do everything right, we won't have to include the units measured here. And then that's moles of sugar divided by 0.15. So this one is 1.86 for the K for water, times 2 times the moles of sodium chloride divided by 0.15 kilograms. Okay. So let's factor out what we know, right? I think that's next. Yeah, let's factor out what we know. We got this one over here and here, this one here and here. So we can factor those two out. So if I factor this one out and this one out times moles of sugar plus 2 times moles of sodium chloride, then this one comes over here as 0.15 times 2.24, and this one comes in the denominator as 1.86. Right? And that's equal to this expression. Well, let's find out what that value is first. We won't have to carry those things around as extra baggage. .1806. So this is 0.1806 equals moles of sugar plus 2 times moles of sodium chloride. Okay. So what we're going to need to do is make a conversion between mass and moles. Only we're going to have to do it with an unknown. The mass of the sugar is X. So what's the mass of sodium chloride? It's 10.4 minus X equals the mass of sodium chloride. Chloride. All right. So now we're going to substitute in here. Remember molar mass. Molar mass is grams per mole. Molecular weight equals mass per moles. Well, we've got moles here. So if we solve for moles, then we got mass divided by molecular weight or molar mass. So it's going to be different for each one. Sucrose, are we given? No, we have to calculate that one. So rather than take up all your time,
342.3 grams per mole. So this moles here is actually equal to mass of sugar, which is X, divided by 342.3 grams per mole. Okay, plus 2 times sodium chloride is 58.44. So that's the mass, 10.40 minus X divided by 54 point, what did I say? 58.44, 58.44 grams. So now what we can do, we've got an equation in one unknown, 0.1806. We got an equation in one unknown. We can solve and find out what X is. And if we find out what X is, we can calculate the percent because we know the total. All we need is what X is, and then we can ratio them to find out the percent. So rather than take up your time doing that calculation, X should be 5.6 grams. You can check my math later. 5.60 grams. So the percent here is 5.60 grams divided by 10.40 times 100 is equal to 53.9%. So that's why it's in the difficult group. Because it takes lots of steps. And you have to use algebra. I mean, well, you don't have to, but that's the simplest way for me, is to use algebra. This is the chemistry that's going on here. And the rest is dimensional analysis. All right. Oh, that's it. That's it for our review, unless you have some questions. If there's anything else yammering on about that you didn't understand or you need elaboration. And we can talk about the, next I'll put the method up here and we can talk about next week's lab. All right, so this is actually going to be 104 L. This is going to be let's see, next week will be the 30th, won't it? Intro. And the lab is going to be molar mass by freezing point depression. Right? Let me pull that one up. Put it on the screen. This is back out here to 4. Freezing point depression. Let's see which one it is. Here we go. There you go. Okay. What for? There. Scroll up just as much as possible.
So what's the objective of this experiment? Think in terms of how you're going to fill out your notebook beforehand. And then we'll talk about, well, actually, we'll talk about the theory right now. See how I make that a little bigger. And I'll have to scroll sideways. There we go. That's probably better focus. There. No, I don't want that. I'm not sure. Thank you. All right. So in this lab, we organize your lab notebook around this lab. You're going to have your title here. That's easy. The objective here, I mean, you can put that word for word. Or you could say, all right, what's the objective of the experiment? To determine the molar mass of benzene by freezing point depression of benzene as a solute in lauric acid as the solvent. Right, so we should have, our pre-lab question incorporates lauric acid and benzoic acid. Not benzene, excuse me, benzoic acid. Lauric acid, benzoic acid. So there's your objective. And you've got a pre-lab question that needs to be answered. Right. So we'll work this one in just a minute. We'll work the pre-lab question. So you're going to have two activities. One is you need to find the freezing point of your solvent, pure solvent, because the method is based upon freezing point depression. And the freezing point of the solvent is your fixed position. And then when you add benzoic acid to it, it will change the freezing point. And that difference is what you're looking for. And it changes that freezing point based upon how much benzoic acid you put in there. Okay. We don't need to go through intimate details, but you're actually going to heat water, lauric acid, benzoic acid. They're both, well, carboxylic acids. I don't need to draw them up there. Lauric acid is a fatty acid. So you probably got a bunch of it in your body already. But this is purified. So you get your water boiling because you want to melt the lauric acid, and then you want to melt the solution with benzoic acid in it. Two different activities. The first activity, you put 8 grams of lauric acid. Now, this can be plus or minus. It doesn't matter. So you would say approximately 8 grams. And then in your data table, you would say exactly how much, right? To at least 2 decimal points. Our balance will go to 4 decimal points, so you can use as many as you want. Then you record that mass. So you're going to need a place in your data table to record the mass of the lauric acid, right? You don't have to write the acid's name on the tube. You're only going to be using one tube. So there's no mix up. Then you're going to take that tube, and they're big tubes. They're bigger around than my thumb. I like to use big tubes for this experiment. About that long. And you're going to submerge it in water and make it melt. And then after it's melted, you reach 60 degrees or 70 degrees, something like that. Once it reaches 60 degrees, you're going to put a thermometer in it and measure the temperature. So as the temperature drops from 70, once it gets to 60, you start counting. And you take the temperature, let's see, you take the temperature every 30 seconds. You read the temperature. So if you graph that, right, time, and you had, right, that's 30 seconds, and 60 seconds, on out.
30, 60, 90, 120 on out. Then you're gonna get temperature over here. And the temperature is going to be, it starts out here, around 60 degrees. And then it's gonna go like that. And it's gonna flatten out. And at some point in here, you're gonna notice melting point. Right? It's solidification point, it's freezing point, this direction, melting point, the other direction, same temperature. So you only need to know that temperature. And once you find that temperature and you observe your lauric acid and watch it, lauric acid is one of those molecular solids that doesn't have a well-defined melting point. That's the problem with this experiment. So if you graph your information, and you may get a straight line here, and you may plot a straight line on this one, right? The melting point is here. So if it's hard to find it there, you just plot that straight line and this straight line across that part of your graph, and where they meet is your melting point. Simply because it's difficult to determine the melting point just by observation for a molecular solid. If it was an ionic solid, yeah, it'd be just sharp as a tack, but not for this. So once you've got that melting point for the pure lauric acid, now you go and you weigh out about a gram of benzoic acid. You know, in this case, in your notebook, you would say approximately 1 gram. And then you would actually write in a place in your notebook in your data, you'd have a place for it, blank, put in the value for that mass. You need that mass because what's molar mass? Mass per moles. So that mass will go into your calculations. And then you want to find out how many moles. Well, the moles we're going to find out by freezing point depression. And that's K value for benzoic acid, and it's in here, right? Back up. For benzoic acid is here. Constant for the solvent, benzoic acid, is 3.90. There. And then this is molality. And that is moles per kilogram. This is moles of solute. This is kilograms of solvent. So when you weighed your solvent out, about 8 grams, convert it to kilograms before you put it in there. And this is going to be your unknown right here. The moles of benzoic acid. So you know this one, you're going to know that one, and you're going to know this part of that calculation, and that's your unknown. And that's what you're looking for. So when you do the same experiment, you add that approximate 1 gram of benzoic acid to your solution, put it back in the hot water, and be sure it's well mixed and melted. And then when you pull it out, you take the same readings again. And what you'll notice is that the freezing point is depressed. It's not here anymore. It's going to be down here somewhere. So this right here is your delta T. Okay? Because your new freezing point is going to be lower than the pure. That's activity 2. That's what you do in activity 2. Activity 3 is what? Oh, graphing your data. So you can do that after the experiment. And this is laid out for you, right? You can just copy that into your notebook, and it will give you places for all of your numbers. Okay, these are post-lab questions. We'll not talk about those right now. There's an appendix, molar mass determination from freezing point depression. It gives a more complete discussion, right, if you want to read that. This also includes a discussion of boiling point elevation. But we don't have to incorporate the Van Hoff correction because benzoic acid and lauric acid do not dissociate.
In other words, we're not putting them in water, so they don't dissociate. They're pure substances, so they stick together as they melt. All right, so let's go back to the top and look at that pre-lab question. That one has to be done, answered in your notebook before you come to class. This shows me that you know how to do the calculation. If you understand how to do this calculation, then you understand as you're doing the experiment, why you're gathering each bit of information. So 7.98 grams of lauric acid. So the mass of lauric acid is equal to 7.98 grams. And that pure lauric acid had a freezing point of 43.75 degrees. Now we're not going to be able to do decimal points. We're going to be lucky if we can get whole degrees with our thermometers. You know what I may do? Since there's only two of you, and you're both going to be partners, I could bring in my electronic thermometer with a thermocouple, and it gives you an extra decimal. So we could maybe do 1 decimal there. And you need to make note of that. If I do that, then when you do the experiment, you need to go into your method, like cross through lab thermometer or whatever you call it, and put in there the actual electronic thermometer that you're using, the model and whatever information you need, so that you can use that same thermometer again if you ever want to do the experiment again. But in this case, we've got a freezing point. So the temperature here, freezing point, equals 43.75 degrees C. Now the mass of the benzoic acid is 1.03 grams. Mass of the benzoic acid is 1.03 grams, correct? Yeah. And the freezing point of the solution, when you put these two together, the freezing point is now depressed to 39.43 degrees C. Okay. And the, let's see, you're given the accepted value for benzoic acid here. So that's so you can compare the value. So let's do this calculation. Right? We're going to need for molecular weight, molar mass, we're going to need mass per moles. Mass is already 1.03 grams. We need to know moles. Okay, so the change in freezing point temperature is equal to the constant times the molality. The molality of benzoic acid in lauric acid. So the freezing point change, absolute value, is this difference with that. So let's do that calculation. 43.75. Let's write it out. This is absolute value 43.75 minus 39.43 degrees C. Absolute value. Then K is 3.90, isn't it? Yeah. 3.90. This is degrees C kilograms per mole. And this is molality, which is moles of lauric acid per kilograms of lauric acid. So 7.98 kilograms, grams is how many kilograms? It's 1,000 times smaller, isn't it, than a kilogram? So we would say 7.98 times 10 to the minus third kilograms. Okay. Now we can solve for moles of lauric acid. So this value, 43.75, minus
39.43 is 4.32. 4.32 degrees C. And then this is going to come over here in the denominator, 3.90 degrees C, kilogram mole. And then this is going to be multiplied by this, right? That's in the numerator, goes denominator, that's in the denominator, goes numerator. 7.98 times 10 to the minus 3 kilograms equals moles of lauric acid. All right. So this kilogram is in the denominator, numerator, denominator cancels, numerator, denominator cancels. The denominator of the denominator is the numerator. So this moles goes up here, and that gives us moles there. So now all we have to do is calculate this one, 4.32 divided by 3.9 times 7.98 and the minus third. Oops, back up. Here we go. So this is 8.84 times 10 to the minus 3. 8.84 times 10 to the minus 3 moles. Right. So this is going to be 8.84 times 10 to the minus 3 moles. And all we have to do is divide that into 1.03. 117 rounded off. 117 grams per mole compared to what? 122. So one of the ways to measure error is percent error. And if you say, what's the percent error here? Well, if we say the accepted value minus the experimental value, then that implies that the error is positive in this case, because 122 minus 117 is a positive value. This is less than 122. That's why I like to say the percent error. This doesn't work in all cases, but sometimes it does. If we say the experimental error, experimental value minus the accepted value divided by the accepted times 100 is our percent error. So the experimental value is 117 minus 122 over 122 times 100. So that gives us a negative value. And that way, the negative value implies that your error is negative. It's less than the accepted value. That's why I do experimental minus accepted. Sometimes that doesn't work, in which case you just make it absolute and say, all right, it was off by this much. But in this case, 117 and 122 subtracted from it divided by 122 times 100 is 4. Let's see, we've got 3 significant figures. 4.10. 4.10%. Okay. So that's your pre-lab question worked out. And that's the same type of calculation that you're going to be doing with your data. And if you get good data, then you should be pretty close. Within 5% is not too bad for a student lab. If your company depended upon it, that would be pretty poor. If your company depends on you to do your best work, you ought to be within 1%. Now, if you're doing work in the field, like I used to do with my growing crops and treat the crops with various fertilizers and so forth, if you get 5% variability in the field, you are doing really good. Sometimes it's up to 15, 20. I've seen 30% variability. Well, that's why when you do field research, especially in agriculture, you need to do several growing seasons. I did 5 for my PhD in order to average out the seasonal variabilities.
That's why it took me 7 years to finish my degree. One of the reasons. Okay, any questions?
And then you've got some post-lab questions that you need to look at. Let's see, other direction. Data calculations. Okay. Exposure thermometer reads 1 degree higher than the actual temperature during the entire lab. How would this affect the molar mass calculation of the solute? This goes to the discussion of random versus systematic error.
Versus random. And that's exactly what it means. Those are good words for error.
If the error is systematic, you know where it's coming from because it happens the same way every time. This is systematic error. You know your thermometer reads high or reads low. Well, in this case, reads high. Every time you can correct for it. In fact, do you need to correct for this systematic error in your thermometer? No, you don't. Why? Because you're interested in change in temperature. Doesn't matter if your thermometer is reading high or low. It reads the same amount both times you make the measurement.
So if your true temperature is this, but you know it's going to be reading high that much, right? So this is the initial temperature, and then, well, actually this is the pure, and this is the solution, right? And you subtract one from the other. That's wrong. Subtract one from the other. This subtracts from that, it's gone.
So it doesn't matter. You can have a thermometer that's off by 5 or 10 degrees. Since we're looking at delta T, doesn't matter. As long as it's systematic error. If you know it's that far off each time. Random error is a little trickier. So random error is always part of your measurement. It's that general discussion of error. You can't get away from it. So what you have to do is manage it. The systematic errors you can manage because you know where they're coming from. Either you can minimize them or you can account for them in your discussion at the end when you draw conclusions about your experiment. But random error, the way we've devised to work with random error is statistics, right? So we have, everybody's familiar with the bell-shaped curve, right? You know, you have your population, this is numbers, and this is, well, some variable, and you have like this. In statistics, that's called the normal distribution. Now, it doesn't always happen that way, but it's a starting point. And the normal distribution is very well known. It's characterized mathematically. And we use it in statistics to help us work around random error. Okay, so that's enough said about that. I've given you the answer to number 1 already. Let's see. I want to make you suffer with the rest of it. There we go. Why is molality used instead of molarity when doing colligative property studies? I've already given you the answer to that, so I'm not going to tell you again. What are some possible sources of error in this experiment? So there you have to think about it. And I'm going to let you do that. Just think about where, especially while you're doing the experiment. You know, what could be off in this experiment? You know, usually error can be subdivided into 2 classes. Either it's instrumental or it's operator. You know, what am I doing wrong or different compared to some other person that might be doing it? Or how accurate are my instruments? So that would inform the answer to this question. Okay, the rest is
a more complete discussion. And you can read that at your leisure.
Okay, I guess we're done.
Well,